Method one is the exact way of doing it. It's a little bit easier to understand this if you look at this this table from method one, because method one, you can't really use method one without some serious understanding of binomial distribution. So so what you want to do is you say, I want to be, so P refers to how sure do I want to be of finding something. Okay, so that's what the P refers to. And the Q in this case is not 1 minus P. Q is the frequency of the allele, of the C1 allele, or if you say I don't have a molecular marker, it's the frequency of the purple seed. Okay, so after 10 years, what's going to be the frequency of the purple seed? Let's say it's 1 in 64. It's not, but whatever, it's, you know, it's 200 out of 1100. And so it's some number, and I want to be 99% sure of seeing that. Okay, so so then you just read off the table. I want to be 99% sure of seeing at least one of these things. So here's the number of these purple seeds or C1 alleles. And so there's one, you can see one of them, two of them, three of them, etc. And what is the frequency 200 out of 1100? You know, it's like 20%. And so it's close to, let's say it's close to 1/4. So you need to look at 11 of 11, these things.
11,000?
Oh, it's 11,000. Yeah, you're right. Okay, thanks.
Where does the 11,000 come from?
Well, it's 200 out of 5,500 plus 5,500.
Oh, yeah, of course. Sorry.
Yeah, that's right. I was saying 1,100, but it's 11,000. So what's 200 out of 11,000? That's not 20%. That's 2%. So that's, you know, that's smaller than 1 in 64. And so you'd read this table and say 99, and so you need to look at 293 to be 99% sure. Now, method two is kind of a very conservative way. So how big does n have to be? Well, you take the logarithm of 1 minus 0.99, okay? And then you divide that by the logarithm of 1 minus 2%, 0.02. And that ratio will give you some n value. It's, you know, I don't know what, it's going to be 400 or so. Somebody want to do a quick calculation on that?
What, sorry?
So if P is in the question, P is 0.99, I think. Where is that? ALA 8? Yeah, ALA 8. So this is the P value, okay, in this notation. So 1 minus P is 1 minus 0.99. So logarithm of 1 minus 0.99, and then you divide that by the logarithm of 1 minus Q. And what is Q? Q is the frequency of this allele in the population. And so
0.18.
0.18, I guess, yeah. And so that
it's 0.018.
Yeah, 0.018. Okay, 1 minus 0.018, and you take the log. So you take the ratio of the log of the first and the log of the second, and that'll give you some n value. And I'm guessing that it's going to be around 500 or so. Somebody tried that yet?
I'm working on it.
Okay.
We got 253.
253?
Yeah.
Okay. Well, I'm off by a factor of 2.
I think.
Yep, I got 253.5. Yeah.
Yeah.
Okay.
I think when I tried to do it in method 3, though, I got 516, but I don't know if I did it right.
Okay, yeah, so then what I'm advising you to do is to use method 3 because method 2 is very conservative and you get a big overestimate. Although this method 2 is the thing that if you, in any of your introductory plant breeding books, method 2 is the method that you'll be advised to use. But so method 3 is, it's actually closest to what the real value should be. So, they said the real value is done with this table 1. And if you looked at the outcome of method 1, I think for them, they were saying, they wanted 15 of these things and they wanted to be 95% sure of getting 15. And so it was around 1,400. And this method 2 gave a value of about twice the number of what you really needed, 2854. So method 3 is 1420, which is pretty close to what the true value should be. And so that's why I was advising you all to try method 3 to answer this particular question. Where did I put that? There it is.
Yeah, I think we got a little hung up on method 3 because it was saying the number of plants required, and we're looking for the number of seeds required. But they're interchangeable, correct?
Yeah. Did I say number of plants in your version?
No, it says that in the SEDCO population.
Oh yeah. Oh yeah. I see. Yeah. They're. Well, it does. Turns out it doesn't matter.
I'm gonna say this out loud right now in case it's being recorded. Zach was right. I don't know if he'll let us live it down.
He should not.
All right.
He wins. But
Right.
really, we all win.
Yeah. All right. Does that help?
That does. Yeah, that's going to be what I need to get through this assignment.
Right. Of course, but then you have to deal with the next one is you have to say, okay, I want to get rid of this purple seed. How am I going to get rid of it for these restaurant owners? And then how am I going to create a population? And this is where I've left it pretty wide open for your interpretation.
Yeah, so like when you say describe, like do you want just theoretical ideas of how you would do it, or do you want us to like prove it mathematically?
Well, I mean, you sort of have to do a little of both. Okay, so you first of all say, so the farm could go out and get a molecular assay, okay? And if they went out and got a molecular assay, then they could, maybe assay all 5,500 seeds that they send off to Mexico to increase. And what they'll do is they'll just assay until they've got 5,500 that don't have the C1 allele, and then send that off. Well, and that's probably the best way, but it's expensive. Okay, so is that something that the farm wants to do? And so for that, I would want you to also say something like, well, this type of assay is going to cost whatever it's going to cost, and some of you may have access to that kind of cost information in the companies you work for, or there are service centers that provide these kinds of assays, and you'll have to go and find out what the cost is to, and you're not going to assay just 5,500 seeds. You're going to assay considerably more than that because the frequency of the allele in the population is such that you're not just eliminating the purple seeds. This assay exists in it's going to detect a lot of the heterozygotes. And so that tells you that you have to maybe, so let's just imagine that an assay costs $10. Or maybe you've got a service provider that says to assay a single allele, it's $2. So I've got to send in 5,500 seeds. Actually, I have to send in more than 5,500. I have to send in how many more than 5,500 to be 99% sure that I'll get 5,500 seeds back from the assay center.
Okay, so that's like with us knowing that only like 0.18% are gonna, no, that's, well, but anyway, yeah, whatever allele frequency,
That's
we'd
right.
have to extrapolate that
Yeah,
into
so there's,
a seed packet that's gonna have to get tested.
that's right. Yeah, so you're going to send them a bunch of seed, and the question is, how many are you going to send them? And if they're going to charge you $1 an assay, you have to look at that and say, well, maybe there's a different way to do this in 1 year. On the other hand, if the restaurant owners say it's worth it to us, otherwise we're going to go somewhere else to get our our masa, then some other organic grower that doesn't have this purple seed in it, then we will do that. And so maybe all whatever expense it is, you can ask for what do they call that? Value added, yeah, a value added cost for my seed. And so, yeah. And of course, once you get it converted, then you can essentially hope. Well, in Mexico, it's probably not a good hope because there's a lot of purple alleles floating around. Just unless you're in an isolation spot, there's a good chance you'll get purple alleles. But it's that kind of discussion that I want you to sort of think through, like what I just gave you.
Nope, that makes sense.
Going back to question 2 with the probability of the alleles, though, we also have to take into account the heterozygotes because we did 200 earlier. We were talking about doing 200 over 50, 200 over 11,000, but that wouldn't account for the heterozygotes that have the C1 allele.
Well, does it? Does it or doesn't it?
The 200, I don't think it would because there still would be. I'm thinking that there still would be that recessive C1 allele.
Okay, so 200 out of 11,000 is the frequency. Let's call it of C. It's C1 squared. It's the frequency squared. Is that correct? That's the frequency of the, yeah, okay. And so what, you're right. What are the frequency of the heterozygotes? But do you really need to know the frequency of the heterozygotes, or do you just need to know the square root of C1 squared?
C1, yeah, that makes sense.
Okay. Although you could figure out what the frequency of the heterozygotes are, beginning with that. As long as you can figure out the frequency of the prickle seeds. Good point, though. Yeah. Think it through.
So going to ALA 9, that deals a lot more with using the Punnett square.
I think you're right.
I just want to make sure for getting the
Oh yeah,
frequencies. Yep.
yeah.
Yep.
Now this is yeah. Yeah, the trick on this one is so the trick on the class notes was that we went from 16 cells down to 9 cells. Well, now we're going from 16 cells down to 4 cells. There's a whole bunch of cells that get gathered together into some of these classes, and there are some cells that only get. They're still, you know, if things were independent, they'd still be 1/16. So which one of these classes here, if they're independent, independently segregating, would have only 1/16 of the total in it?
The recessive.
Yeah, this one down here. So that's the one that should have only 1/16 if they're independent.
Right.
And that actually tells you a whole lot, just like that purple class we were talking about. That double recessive is a clean estimate, provides you a clean estimate of the allele frequencies for these small letters, if you sort of think it through.
Mm-hmm.
But you have to sort of think about, is it in coupling or in is or repulsion phase? Are those terms? Are you comfortable with those terms?
I understand them. Calculating them might be take a little bit more thinking, but
yeah, and so you just have to say, well, if they're in repulsion phase, then that means this double recessive thing here. What would it look like if they were actually on opposite chromosomes and you had some recombination or no recombination? I mean, not no recombination, or recombination of 0.5. And it turns out that either one of these, either coupling or repulsion, and I won't tell you which one, is impossible if you see 18 of these. So the only way to get it is with one of these. The only way you can get 18 is if you have either coupling or you have repulsion. So that's what this hint is about. So if you do have coupling, you know, what is the expected frequency if these things are independent? And that'll help you figure out whether or not they're in coupling or repulsion. And once you've got that they're in coupling or repulsion, then you can start assigning recombination values. Yeah, the ALA 9 is actually, it'll take a huge amount of thinking and not a whole lot of calculation.
Well, that's actually some pretty good hints then.
Okay, good.
Now, is 10 supposed to be really involved, or is it actually fairly simple? It looks a little deceptively simple.
Yeah, it's pretty simple. After you've done 9, it becomes straightforward.
Okay.
So that's why you added the third assignment for this week, because the third one wasn't going to be that big of an ask?
No, not really.
Okay.
In the past, I've done ALA 7, 8, 9, and 10 all together at one time. So we've managed to get 7, which is, as you found out, is really pretty simple anyway. Um,
That was a nice assignment.
yeah, right. Yeah, and I don't think. Well, maybe I told this group before. Maybe I just told it during the other with the on-campus students, but that particular that set of pictures and all that stuff was all built by students from this class about, I don't know, 8 years ago probably. I just asked them. I said, would you guys think about making this more interesting than just a bunch of equations? And they did. They came up with a really nice set of pictures and made it a little more fun. Any other questions? By the way, I'm a little bit behind on grading the last two ALAs because I really wanted them to be done today, but our students, the on-campus students, which are mostly PhD students, have a symposium tomorrow, and it's called the R.F. Baker Symposium, and it goes on all day, and anyway, it eats up a lot of our time in the week beforehand, and so I'm a little bit behind on getting your grades done from ALAs 6 and 7. And then tomorrow, when I come in to give at noon, I may start out a bit late because this symposium is on another part of campus, which is about a mile away. And so it's going to take me a little while to dash from there over to the Breton Center for reporting this. Any more questions, or should I leave you to your own discussions? Okay, I'll leave you all to carry on.
Thank you very much.
Yeah, thank you. Bye-bye.
Bye.
Bye.
So is everybody going to be on here for a while?
I'm hanging out all night. I just ordered takeout.
I'll be on. I do have a question. So since I showed up a half hour late, I didn't want to ask, but how did you guys come up with the 200 for year 10 and then do 200 divided by 11,000 to get your...
It's the number of alleles. So it's 100 purple seeds, so 200 alleles.
Oh, okay. But, so then how do we change that for like year 3, 7, and 10?
It sounds like the population is, because it's such a huge population, that it's going to stay in equilibrium.
Oh, okay.
That's kind of what it sounded like he was getting at to me. Correct me if I'm wrong, anyone. I like being corrected.
I still did that number times the 1 minus the, or what was he saying earlier? He was saying,
Yeah, because it's like 1 minus the number, but to the 10th power because it's over 10 years.
Okay, I'm sorry. I didn't get to hear what was the question that was asked.
So we're talking about question 2, assignment A8?
Yep. He was saying, and you guys tell me if I'm wrong, there's no selection pressure, so the C1 allele will exist exactly the same as what it is at the beginning. Because I asked him, I said, we don't need to use the Fisher table then, and he said no.
It didn't
not
really
for
sound
question 2, or not
For
for
question 2, the probability of the C1 allele existing in the population with 0 selection pressure in 10 years is the same as it existing at year 0.
Yeah.
Okay, so then when you move into 3, really 3, 7, and 10, we're using the same Q.
Yeah.
Okay.
Mm-hmm.
Okay, that's what I was wondering. Thank you.
that part I'm confused. So 3, 7, and 10 were using the same cube. That means we would have the exact same values, though.
We'd have the same frequency, but we want to sample for. Well, yeah, you're right. It should be the same.
So that's where I was thinking then whatever he was talking about came into play, like the square root of, or squaring it to the 10th power, or. But in his example, where he squared it to the 10th power, I forget what he squared it by, but I think for the 10 years it came out to like 0.2% or something.
Yeah, the frequency is at
0.02.
Yeah, that's the same as starting at 0. It's 200 alleles out of 11,000 alleles is 0.018, or roughly 2%.
Oh, I see what you mean. Yeah. But then if you square that, you get 0.135, which would be the frequency of the C1 allele.
Right. Well, is that true? If the frequency of the allele is 200 out of 11,000, isn't that the square root? Because it's you're already taking the both alleles, you're accounting for both alleles. Or am I wrong? I'm wondering if he wasn't confusing with 100 out of 5,500, because the 100 represents both alleles and you need to take the square root of that, right? I'm just wondering how that works. Because I could be out to lunch. Because I know where you're getting your 0.135. Because you're right, that should be, I mean, that's how I was calculating it earlier. I did a quick estimation, and that's how I figured out the frequency of the heterozygotes. But the A allele itself should, like you said, be 0.135 if the frequency of the recessive, I don't even know how to say it, the recessive homozygote is 2%, then yeah, the A allele should be 0.135.
That's what I'm thinking.
Okay.
Okay, so you're thinking 0.135 for, are you talking 2 or 3 on this?
2.
Okay,
Yeah,
so you did.
He wasn't giving us straight answers, is what I'm saying.
Okay, gotcha. So you were thinking, though, 200 alleles divided by 11,000 gives you the 0.018, and then the square root of that gives you your allele frequency 0.135.
Yeah.
Well, that's why I'm wondering. He kept talking about 200 out of 11,000.
Yeah.
Which is accounting for all the alleles, and that's 2%. But then we're talking about, which is the exact same number as 100 purple seeds with both alleles divided by 5,500 seeds. That's
Then
still
I
an
asked
allele
him-
frequency of 2%.
Yeah, because then I asked him, how do you account for the heterozygotes? That's when he was kind of hinting you would square it.
Okay. I didn't catch all
thought
of that.
it
So,
didn't-
no, I didn't catch
I
all
don't
of that.
know.
That's why I'm asking.
It was a little confusing, so I just don't know. I'm hoping that's what he meant.
So you're thinking your final probability that the C1 allele exists in 10 years is 0.135.
Number 2, yeah.
Yeah. Okay. But then you're using that to plug into. Are you just using method 2? Like he was. That I kind of came in just as you guys were practicing that one.
I think he wants us to do all 3 of them. It's almost what it sounded like.
Not really though, because he was like,
3.
yeah, he was like 2 is what you would have done in every other class, and 1 would be easy, but we're gonna do 3
Okay.
because it's the truest value that.
Yeah, that is what he said.
I think he also mentioned in another class that he wanted us to use method 3.
Yeah.
Yep.
He's talked about it a couple times. He likes it.
It just bugs me. Zach was totally right, dang it.
But we had a
Yeah,
great
I'm just
philosophical debate.
I'm just wondering for question 3 if I'm getting the right Q value, if I'm figuring out Q correctly for 3 years, 7 years, and 10 years. It's got to change, right? Wouldn't it?
Well, you'd think so if he's going to ask us for it, unless
Right.
it's a trick. He's not above tricks.
Yeah, and I thought that was the whole point of going over the table and how we got it, the Fisher table or whatever.
Yeah.
So what I originally did was I did the 1 minus whatever the number in a Fisher table was with no selection for, say, example, for 3 years, and then multiplied that by the frequency of the allele, which is 0.135, and I got 0.05 as my Q. But I don't know if that's what everyone's thinking.
Okay,
or
yeah,
if there's
here's the
something
thing.
else.
When we were doing the method 2 with him, and we did the P and Q, he had us use a Q of 0.02, and that's how we got that 285 or 253. And he was agreeing at that point. So if we change the allele frequency instead to 0.135, which I understand, then all of a sudden we go down to 32. As long as we're happy with that for method 2.
Method 2, yeah. What, I don't know. Method 3, I get a lot more than that.
Yeah, well, the thing with it is that I just want to see if we're agreeing on the same Q value of 0.135 instead of 0.02. That's it.
Yeah, because the 0.02 would be the frequency of the purple seeds, not of the allele.
Right. Even though he was doing the whole 200 out of, and I didn't think that was right. That seemed too simplistic. 200 out of 11,000.
But I didn't use the 0.135 for my Q. I still multiplied it by 1 minus the number in the table, depending on what year you're looking at. 1 minus.
For each year. So for the third
For
year,
each year,
that
yeah.
becomes your Q.
That's
your
what
modifier.
yes. So it would be like 0.05 for.
Yep.
3
0.05, 0.03, and 0.02.
Yeah.
Okay, and that's where.
That's where I'm not sure.
He was being real wonky about that. He showed us the table and how to derive it, which was fine. That's the Fisher table, but he was not. That question 2 kind of threw me. I'm almost certain that what he said is the frequency of the allele after 10 years in the population is going to be the same as what we start with. Did I mishear that?
That seems right if it's in Hardy-Weinberg equilibrium.
Yeah, he did say that for number 2, so I don't know why. But then number 3 wouldn't matter how many years.
Yeah, I think that if you put in question 2, if the population is in Hardy-Weinberg equilibrium, then the frequency after 10 years will be the same. That's with 0 selection pressure.
That makes sense.
I don't know.
So then, does the Fisher table only come into effect if it's like a small enough population? Is that what we're saying?
You know, that's exactly what I don't know.
Yeah, because when do you use that then?
See, I thought that was the probability of loss in any generation of an allele, and that eventually the allele, because of a small population, but nobody ever says what small is.
So I'm going to backpedal to question 2, just to make sure I'm following what we think is going on.
Yes.
I think we know.
Yeah. So there's 200 copies of the allele in the purple corn. So are we counting, like, are we doing the probability of, like, the purple and then the probability of the alleles in the het and adding them together?
Well, if you get the probability of the purple seeds, then if it's in Hardy-Weinberg, then you should be able to use that to get the frequency of the heterozygotes, right?
Yeah. So the way that I went about it, and I'll share my screen. You guys can see how I did it. It's not that.
Yeah.
Thank you.
I'm visual. I love seeing.
Can you see this?
It's a little tiny, but I can blow it up if I take a
Hold
screen.
on. I don't know why it did that. There. That better?
Still pretty small.
Okay, I don't know why.
That's okay.
Anyway, so the 0.02 is 100 divided by 5500. That's your frequency, and then you take the square root of it to get your allele frequency. And then that means that for the large A, it's 0.87, should be 0.13 or whatever you want to work it out with. But I take that number and I square it so I can get my 0.75. And then that should give me my heterozygote, right? 2 times the large A allele times the small A allele. I mean, it's all real basic. And that's how I got my heterozygotes and homozygotes. Basically, P squared plus 2PQ plus Q squared. So, yeah, this is a real basic question that I wish he had answered better.
Mm-hmm.
All right, so I got to jump off for a little while and go watch a basketball game. I'll be back in about 45 minutes.
Sounds good.
I'm just going to mute it.
So confusing.
Yeah, I'm struggling a little bit. Like, that last part makes sense. I'm just confused. So, like, that gives us our allele frequency, right? So that answers number 2. We just post that, like, really the 0.135 is our allele frequency. So we can show... Now, go ahead.
Oh, but for 2, we're looking at the probability that it will exist. Not what frequency.
Yeah, when he talked about it during the lecture, he kept, like, referring to it as frequency.
Yeah.
Yeah, I can't see what Jacques' table says anyway. I tried to blow it up, but it's so blurry.
He basically just had the 100 over 5500 to get the 0.2 and then the square of it. And then 1 minus that number for the A, big A frequency.
Okay, so 0.18 times 0.18. .033, and then 1 minus 0.033.
How'd you
Wait,
get...
what?
0.18 times 0.18.
0.018, wasn't it?
Oh yeah, 0.0.
Okay, that changes everything.
And the square root of that. I say root. Everyone else says something else.
Yeah, I did square root of.
Everyone keeps saying root, and I didn't know if maybe that was like an American thing to say it that way, or if I'm just saying it wrong my whole life.
Everyone I know.
I definitely say root.
Oh, really? Okay.
But we're both Canadian, so maybe it is just an American thing.
Oh, no. Rut is when the deer mate. Okay, so I should have that 0.0000324, and then you take the square root of that.
What number do you have?
0.018 squared.
No, square root of that. Square root of 0.018.
Oh, square root. I was squaring it. That's why I was getting this infinitesimally small number.
Yeah, because the 0.018 would be equal to p squared.
Yes, this is all coming back slowly. He's presenting it in a really ugly way.
I agree. I think he presents it really confusingly.
Yeah. Like, I've done all of these things before, but it's all gone. I don't remember. Okay, and then it's going to be 1 minus 0.134.
Yeah.
Which is 0.866. And that becomes P. Well, not really P, because in the next case, that's going to be probability. N. No, it's not N. I don't know what it is. I'll just say allele frequency. I need those half marks. So for question 3, are you assuming that you're using markers or not?
I think not, but
yeah, because he said like it's a possibility, I guess, when you go through your mental process as to how you're gonna do it. I'm tempted to say not, because then you can just rely on like the laws of.
Right.
It almost seems easier.
Yeah, because it's going to be so much more precise with markers, so I'd rather not. Kick it old school.
Okay, so just to go back to 2, so we have those frequencies figured out, but someone said, like, he's asking for the probability, not the frequency. So how are you reporting just the probability then?
Yeah, so like I showed my math, and then I guess instead of allele frequency, I should just say like, we should say that it's the probability.
They're using the 13-point problem and just calling it the probability instead of the frequency.
Well, that's what I was putting down at first, and then I don't know.
I thought he made a comment though that he said, so that will be your probability. That's the frequency, and that will be your probability. But I could be wrong.
I was just trying to distinguish if they're 2 separate things he's asking for, or if it's really the same thing.
Yeah, I'm not 100% sure, but that's what I thought he had said.
Okay. I'm good with that.
Listen again.
I'm good with that.
So I just missed that because my cheeseburger just showed up at the door. Heard the knock and I had to run. So we do the math and we're just saying that our value is the probability.
Yeah.
I was just saying I thought he had made a comment to the effect that the frequency would be equal to the probability. But I could be misremembering.
He seemed to be using some of the terminology pretty loosely, so.
Yeah.
That's fair. Okay. So then moving on to 3.
I'm ready to move.
Okay. Okay, so for 3, we were still using method 3, right?
Yeah.
And using the Fisher values is probably our best bet to get year 3, 7, and 10. So, Tiffany, I saw you posted on the discussion board, and you had smaller values than what I originally had. So how were you coming up with those? So, because what I had just done was I had done like 1 minus the value on the table.
For Q.
Yeah.
So that's where I'm not sure. So I did 1 minus the value on the table and I multiplied it by the allele frequency of 0.135. That's where I'm not sure if that I'm supposed to do that or not.
I guess why were you thinking multiplying it by? And I honestly do not know.
I think we talked about. I think in our last office hours, for some reason, I can't remember why we were multiplying it by the frequency of the allele. So that's had stuck in my head from the last office hours. So that's how I was doing it, but I don't know if I need to do that.
Now that you say that, I think I actually did do that in part of the manuscript or whatever that he showed us with all the different methods. Because I used that later on when I was trying to answer number 4 for the expected frequency of allele in year 10. I did what did I put? I multiplied it. I don't know if I have it totally right, but I did multiply it by the 0.16. And that's where I got it from, was that manuscript.
Yeah, in the population genetics paper, you mean?
Well, what is it called now? Sorry, I don't have it pulled up here. The one where it talks about all the different methods.
That's cool.
Oh.
Yeah, that one. I'm trying to find it now, but now I can't see it. So maybe I have it wrong. Maybe it wasn't that one. Maybe I saw it elsewhere.
In the population genetics, like page 13, that shows like multiplying the allele frequency. So like it uses the original frequency from generation 0, and that was 0.005 in the example, and then they multiplied it by the probability of the allele and generation 10. So that's where they're doing that.
That's just okay. So is that different though? Because they're multiplying it, the frequency of the allele, and what are they multiplying it by? Oh, the probability after 10 generations.
Yeah.
1 minus the. Okay.
Yep.
Yeah.
So I think that's what you guys are doing, right?
Yeah.
Okay. And then that just becomes your Q value for each year, and then plug it into that method 3 equation. Okay, I think that. Yeah, I think that makes sense, or I'm happy with that as an answer.
Do you guys know if we're recording this?
I think Lawrence was.
Okay.
But I don't know that for sure. I just thought, based on the discussion, he said he could help because Zach asked somebody to.
I have to go, so I'm gonna watch the recording later because I'm gonna need it.
Sounds good.
See you guys. Are you guys gonna be on tomorrow? Or not tomorrow, Saturday? Or maybe tomorrow?
I can probably be on either. I will Saturday for sure. If somebody wants to get on tomorrow, I probably can for a little bit.
Yeah, I'll probably be a little bit of both.
Okay, sounds good. I'll talk to you guys then.
Okay.
Bye.
Have a good night.
So do you guys have n values then for if you use that as the Q?
I'm still not really started on that one yet. I'm trying to figure out what equation still.
I just tried it. I think I need to redo it because my number is probably way too high. It's like 18,000.
I just plugged it in and I got 121 for 3 years, 220 for 7 years, and 293 for 10 years.
So what did you try to get those values?
That was just plugging it into method 3 equation using that Q value that we just talked about with the, what is it? The 1 minus whatever year on the chart from Fisher times the 0.135.
Okay.
Okay.
Let me get my calculation. My Excel kept coming up with random numbers the other day that seemed off, so I think my parentheses are off somewhere.
Yeah, it took me forever to put the formula into Excel the other day and get all of the brackets and everything in properly. I double checked it with using the numbers that they had in the paper, so I'm pretty sure that it's in right now. As long as I actually have the like Q and everything in properly.
Are you using 293 for R? Chelsea?
Oh, no, I did not. So wait, why is it 293?
Because if you look on the SEDCOL table, what he was saying in the discussion was that we only need one plant or seed recovered, so R would be 293 because the number we have is closer to 1 out of 1/64.
Because I thought R was just 1, because you're looking for one allele.
That's what I thought too.
Yeah, that's what I was using.
Oh, I thought he was saying to use that.
So I thought R would still be like the 1 to 15, but then the others would be the population that you would need if you went off that chart. But instead of going off that chart, we're calculating the number of seeds. Is what I was thinking.
Maybe he was talking about the first method when he said that.
How's it going, everybody?
It's going.
How are you doing?
Oh. I'm okay.
Sounds about right.
So did Dr. Beavis mention at all that if these were diploids, or are we just assuming they are?
Was not discussed.
So in the chat area, I see somebody, or Cassandra, you wrote there are 200 copies of allele in every subsample. Frequency will be 200 over 55,000 or 11,000.
Yes.
That's
We got to the square root of that. Ha ha ha.
it's the square root of that.
So it's like 100 over 55,000 is 0.18, and then the square root of 0.018 is 0.0134 something. So the probability of finding the allele ends up being 0.135. I'm going to copy that logic into the chat window. There.
Oh, gotcha. Yeah, because she's. You know, I was going to use the in I don't know if this is even valid, but the book of cultivar development. Didn't Dr. Fair have a table in there with like the frequency, the PQ, and R, and all that stuff?
Yeah. Well, and we went over that in the discussion today too, and I think that's kind of like the method 2.
Oh, it is?
Yeah.
Method 2. What's the, well, I guess, what's the third?
From the
or
schedule paper.
What's the first and third method then? Because I heard that earlier.
Yeah. The third one's the one we're supposed to use. The first one is just kind of an easy calculation.
I thought the chart was the first one, and then that.
Oh, yeah, you're right, Chelsea.
Yeah, then that easier calculation is method 2. That's really conservative.
Then what's the third one?
If you look on the paper that he posted, that's what is it? Sedcol.
Oh, hold on. Oh, Sedcol.
Yeah, it's listed in there. All the methods are listed in there.
Oh, there's that chart. Oh, okay. Method 3.
Yeah, I got to figure out how to plug that bad boy into Excel, which sounds like Chelsea had the joy of doing already, and a couple of the others of you.
Oh, really?
Whoops. Oh, no.
Is it easy once you get it in Excel then, I'm assuming?
Yeah, it's
It
not.
probably makes your life easier because then you can do it for the 3 different ones with just like dragging it.
Yeah.
Yeah, like what's Z? The normal deviate.
That's that number
for 99, it's like 0.99 or 0.95.
Mm-hmm.
I don't know exactly where it's listed on that sheet, but for 0.99, it's 2.326.
So that's not in the SEDCOL paper. That's in the like class write-up.
Oh,
It is in the SEDCOL paper.
Okay, yeah, because I'm looking at that table.
If you go to the paragraph about method 3,
Yes.
Mm-hmm.
it's in there.
Oh, Z equals 1.645. Or
Yeah, ours is 2.326.
yeah. So for Q, are you guys using 0.018 or 0.135?
I had 0.018.
Okay.
Because aren't we saying that each year would be the same?
Yes, that's what we just got.
I thought somebody was saying something different.
So I was thinking after talking with Tiffany, she did something different. So she took like the table from the Fisher table value, so 1 minus like year 10, 0.84, and then got 0.158, and then multiplied that by the 0.135.
Would you be able to type that out? I just have a hard time understanding numbers when I hear them. Sorry.
Yeah, I can share my screen too. Okay. So what I was thinking was, so from the Fisher table, do the 1 minus the Fisher table value for the generation. And then, so that second part, what Tiffany was saying was that they were talking about multiplying it by the 0.135 to get the final frequency. And that was where that was coming from, the Population Genetics Foundation, like class notes or whatever, where they were multiplying the probability of the allele by the allele for that generation. Was why they were multiplying that. Now this is still off.
But from what Beavis was saying, it sounds like no matter what year it is, unless you're actually trying to, take out the purple seed, the frequency should stay the same.
Yeah, that's kind of what I gathered too. So I found it really confusing that I guess we've talked about this a bit already. Why does he want the 3 years? Like, how are they going to change?
Mm-hmm.
Other than if we incorporate that.
The Fisher table.
Yeah.
Yeah.
Unless he's just trying to prove a point that it won't change.
Yeah.
Because he basically said that we should assume it's in an equilibrium and it wouldn't change over those years, right? Is why you're thinking keep with this value.
Yeah, that's what it sounds like he was saying.
Okay. I came in towards the tail end of that.
Because the whole use of the Fisher table was us trying to figure it out on Tuesday.
Mm-hmm.
So maybe we were just on the wrong track then, and we don't need to use that at all. I don't know.
It doesn't really sound like we do. We're just there to like throw you off.
I guess then my question is just when would you use that table? Because I mean, the one column is for if there is no selection advantage.
Well, and is selection the same as selection advantage? I don't know if I 100% know what that means.
I would assume it would be the same whether it's like a natural selection or an artificial selection. It would still be like a selection advantage, I guess.
Okay, because it is in regards to the allele.
True. Yeah, I'm not sure. I'm confused by the Fisher table.
Well, like if you look at this section where it's mentioned, it's about fate of a single mutation. I don't know if I don't think this was really a mutation.
So would that be just like one single allele in the population?
Maybe that's what that is.
Maybe we're supposed to put that one in the bank till exam number 2.
Yeah.
Yeah, it just seems weird to have us do all 3 generations when if it doesn't change.
Is there anything? I haven't looked at the discussion board in a bit. Is there anything mentioned about it, or is anyone who would?
Not since Tuesday. Like there hasn't really been a reply to that.
Oh, okay. No one wants to answer it.
I know.
So are you guys thinking then that you would just use the 0.135 for the Q for each generation?
I thought we were talking about using 0.018.
So I thought that was the frequency of purple seed, not the allele. Because square root of that would be the frequency of the allele, right?
Oh, yeah.
You're right, Chelsea.
Yeah, that makes sense.
If I plug in 0.135 for my Q, I get 42.
I'm typing in that equation, and I've almost finished typing it in, but I'm kind of not sure how to type in half. Like at the end of the equation when it asks for half of that back portion.
I'm thinking if you just
Do you do the caret and then put 1/2 in parentheses?
All right, so is the caret, like if you have like squared, you would just put caret 2 in instead of double typing it in brackets?
Yeah.
Okay, because yeah, like I'll put it into the chat window what I have so far. It's scary. All right, so now I've cleaned it up to that. Oh, it doesn't work anyway. There's a problem.
Yeah, I kept, every time I thought I had it right, there would be, I tried to put it in and it would tell me something was wrong. Once I finally got it in how I thought it was supposed to be right, I tried plugging in the numbers from the method 3 example in that paper to see if it matched.
Mm-hmm.
And so once it finally matched, then I was like, okay, I think I have it right. Now it's just a matter of getting like the right Q value or whatever.
Yeah.
pretty sure when you plug in the equation into Excel and you use the Z as 2.326, the R is 1, the Q is 0.018, and R is 1. I think I might have said that already. Z squared is 5.41. I got 0.11146. Does that sound about right?
That
I'm
was
fighting to
huh?
I'm still trying to type it into Excel, so
That was your final answer?
Well, no, that's what I got for the equation when I utilized those numbers.
Oh.
Does that sound about right to you?
It should probably be larger because we're looking at number of seeds needed.
So you said, well, your Q value was 0.018. Z
Right.
was 2.326 and R was
Right.
1.
Right.
And you got what?
0.11146.
And I got 42.
Oh, what the hell?
I also have 42, but that's using a Q value of 0.135.
Oh yeah, I used 0.135 also, sorry.
I still got it. When I switched the Q value, it got 0.72. What am I doing wrong?
Is it your brackets? I know that I had a lot of problem with my brackets, getting them in right.
No, well, I'm using parentheses, but maybe I have to use brackets. Just trying to avoid that. Just trying that out. Z. Z squared. B2. Oh.
yeah, I do not know what I'm doing wrong with this equation, but it is not having none of it.
I used my calculator when I calculated just now. Because, yeah, mine keeps not coming out, so I'm trying to get it into Excel still. But I kept getting way smaller than what I thought.
Yeah, like I might just have to do this like algebra by hand with some.
I think I know what I did wrong. Need to put the Z squared in there. Oh.
I posted there what I used in the chat.
Ooh, I'm gonna compare and see what I am doing. That's so weird. Okay, so you didn't use the like weird like face bracket.
Oh no, I just used regular brackets, round brackets.
Huh, that's what I had before. But I might be. I think I figured out what I was doing wrong. Damn. Well, numbers climbing slowly. I'm up to 1. 2 times 1 minus half plus z squared. So I'm just gonna do that times 1 minus that.
I finally got it, and I got 42. So.
Oh, damn you. Rubbing it in. Damn it. I'm on a mission now. B2, which is...
Okay, and so then you're not thinking anything changes for the other generations still?
I still think it doesn't, based on what you said.
Okay.
Yeah, and that makes sense if it's in Hardy-Weinberg equilibrium.
Yeah, like it's the perfect genetic population that I wished would have existed in my undergrad.
Sweet.
How'd you do the half, shit. The half within the equation? How'd you do that in the...
0.5 hi-hat.
That's what you did?
That's what Chelsea did. She got it to work.
Somehow it just got placed. Oh wait, I was looking at the wrong one here. Oh. Oh my god, I got 84. Too much.
You
All
got
right.
At least you know there's an extra multiplication of 2 somewhere.
Yeah, where is it? There's a times 2 in here somewhere. Plus d squared, or d2, which is right. Plus 1 minus plus b2, then d2, 1 minus to the second power, plus 4. I think I figured it out. Oh my god. Nope.
I did it.
You.
I got 41.7.
Yep.
Alright, I'm half tempted just to start over here. Okay. 2. C squared minus that.
So would number 4 then just be still the 0.02?
I think so.
Yeah, that's
seems-
what I was thinking.
yeah. It seems so like oversimple.
Oh my god, I'm going nuts here. I got 61 now. How did I get 61? 2 times 1.
Okay, so after we solved for n, did you guys just put a little blurb being like, this is going to be the same for all of them because of Purdy Weinberg?
Yeah.
That's what I have right now, yeah.
Could I ask a favor? If I share my screen, could you guys look at my equation and see if you see something I don't?
Sure.
Um, it looks like the very last part, that should be on the outside, the 2 times B10. You should have the parentheses before the division.
You mean the back parentheses?
Yeah.
No. And do I just get rid of that and try it?
Because that's supposed to be
No.
separate from the whole first part.
I mean, it should be. No.
So the only difference I think I'm seeing is so where you have the second D2 in your equation.
Yeah.
After that.
Which is this section.
Yeah. I'm thinking there's more parentheses in that back section. Okay, try putting parentheses around the 4 times the 1 minus B10.
So if I had somehow I got 61 before. 2 times 1 minus half plus D2, which is that R or Z squared, times 1 minus Q. Maybe I have too many parentheses? No. So frustrating. It's B2 plus Z times Z squared 1 minus Q squared plus 4 times 1 minus Q, just straight up times 1 minus half. Huh. No idea.
Oh, wait a second. 2 times B10. It's 2 times Q. They're not 2 times Z at the very end.
Two times Q?
Yeah.
Which is that? It's that one.
Yep.
Isn't that right?
Okay, sorry. Then I was looking at the wrong line. My bad.
That's all good.
Yeah, I don't know. It looks pretty close. Like, it's only
If
a
I just
parenthesis.
write it
Yeah.
out. If I just write it out.
I just wrote it out because I just didn't want to make it more complicated than I needed to.
Was trying to be fancy. Oh, that's 4. Sweet baby Ray. You definitely may need to step away for a while. This is just unbelievable.
The one Chelsea posted works.
Which one? On the discussion?
The last one in the chat.
Yeah, were you trying to follow mine? Mine's broken.
Oh, we'll hold on. I'm gonna take a snapshot here and see if I can copy it and if it works. What am I doing here? I'm gonna laugh if it doesn't work and I get the same 76 number.
Maybe you're in a time warp and your seeds are different.
Plus.
All right, I'm back. What'd I miss?
Me being very frustrated.
Aren't we all?
Celebration and heartbreak. I think that's what happened.
What's the matter?
Well, what's E21?
The frequency 1.35.
Oh.
So are you guys on ALA 8 or have you moved on?
We're still 8.
No.
We spent some time discussing question 2
And
and how we get to that number. So we settled on, I have to go back now and look, 0.135. Everyone seemed happy with that.
okay,
And then we moved on to question 3 and decided that 3, 7, and 10 years are all going to be the same value. It's in Hardy-Weinberg equilibrium with no change.
okay.
So we
Yeah,
got it.
I'm with you. I am
Yeah.
absolutely with you.
Awesome. So 41.75 is what we were getting for n after typing the method 3 equation into Excel.
Okay, that's where I was going to ask you guys, what did you guys type in for that? I wanted to make sure I got that right.
If you look in the chat window, don't look at what I did. That's bad. That's bad. But what Chelsea typed in works. You just have to sub in for like the E21s, whatever your
Yep.
cell is, or manually
Okay,
type.
okay. I'm just going to compare it to what I've got on mine because I wrote it in like Zach did the other night and I wasn't sure if I did it right.
I will say
Okay.
this is an exceptional amount of quote parentheses.
Yeah, that's exactly what Zach said the other night too. So
Hey, oh my God! What the hell did I do wrong?
I just went crazy with them to try to make sure that it was using them correctly, if that makes sense.
Yep,
That's
and
probably-
E20 and now I want to get this sure if I got this right. So E21 is going to be the frequency of the A allele at 0.135, correct? I'm assuming that that's what it is because that's what it should be.
Sorry, can you repeat that value?
E21 in the formula that Chelsea gave us should be the frequency of the the small A allele at 0.135.
Yes.
Yep.
Yeah.
Okay, I've got it right. And it looks beautiful. Good job, everybody. Did you all type it in so that he could see that you did the work too?
I did type it in to validate my own self of academic skill. Yes.
Okay, so for number 2, you guys are saying if the population is in Hardy-Weinberg equilibrium and there is zero selection pressure, although I suppose if it's in equilibrium, that kind of says that.
And random mating.
Isn't that a part of Hardy-Weinberg? Isn't that one of the assumptions?
Okay, yeah, I guess it just depends how you say it. Like I said, because it's a large population that's randomly mated with no selection, it's in Hardy-Weinberg equilibrium.
And it's the frequency of the genotype is 100 out of 5,500.
Yes.
Why are you laughing?
Because I'm still getting the wrong number on my old equations.
Okay, so I'm just double
It's all right.
checking. This is what I've got. If the population is in Hardy-Weinberg equilibrium, then the frequency of the genotype is 100 out of 5,500, or roughly 2%. To account for all alleles in the population, the square root of 0.18 is used to calculate the frequency of, or the total amount of the allele, which is 0.1, or the total frequency of the allele is 0.135. The total frequency of the small a allele.
Yes.
Yeah.
Gotta ask, why rut, not root?
Did I say square root?
You did.
I can't speak then. It's because apparently my lips are freezing off. I don't know. It's
No,
square
I'm just
root.
curious. Because a
My
bunch
root.
of people in the past say rut.
Yeah, Dr. Beavis also said it.
I say root, and I'm American, so
I should be saying square root. I don't know why I said square root.
you've been listening to Beavis, that's why.
I think I'm just tired. It was a game. It was the last basketball game for my son for the season, so not emotional, but just kind of I wanted to get back and get this done and be done because I'm tired. Supper's calling. Be right back.
All right. Well, now that we got Jacques up to speed, or how's everyone on question 3? Are we ready to charge onward?
I'm
Yeah.
5, yeah.
Yeah, I'm ready to go on to 5. Because 4, you guys just said basically what we already found in 2 was that 0.018 is what we said was the purple seeds.
I'm giving up.
Yeah. If the allele frequency is not changing, then that shouldn't change either.
Okay.
Yeah.
Good there. And I was moving on to 5 also. So yeah, I guess I'm working on talking about the marker assisted selection. And then also, didn't he talk about like phenotypically selecting the seed also?
Yeah.
So those are the 2 that I've got a little paragraph on right now.
And then he also mentioned something about like going through the field after it's implanted,
Yeah. For
a machine to remove plants.
number 5, I thought you'd just go and call plants a purple seed, because that would get rid of the purple seed from the harvest.
Yeah.
you just answer the next part that it wouldn't eliminate C1 allele.
Yeah.
But
he said on
Oh no, go ahead.
He said on Tuesday that you should have like multiple possibilities for 5.
Oh, okay.
Yeah, and I was thinking if you really wanted to eliminate, like you want to eliminate purple from next year's harvest, like marker assisted selection would still do that, and it would eliminate that allele from the population if you got rid of everything with that, right?
So we could maybe give an example of like marker assisted versus non-marker assisted.
Yeah, so that's where I'm at.
That wasn't he going on though about how you'd have to like go figure out what the costs and everything would be and explain that?
He did, yes.
It seemed very like not what the question even asked.
I know, that's where like I have an unlimited budget as far as I know, so it's not a problem.
When he was saying that, I was like, if I wasn't here listening to you tell me this from what the question says, I'd have no idea that that's what you expect.
Yeah. I might just say you have to take this into the cost into account for this, though, if you have the budget or not, and not find actual costs, because, I mean, then you get into, okay, which method, and...
Yeah, because for that question number 5, I was thinking about markers, but I was like, that's a lot of plants to do markers on.
Yeah.
Well, and then having the access to like, would you need seed chipping to do mass on the seed and then plant it as well?
That's what I said for number 6, I think, was to use seed chipping. Because then I was like, it wouldn't be the whole, 200,000 plants or something. It would just be, I don't know. And then he was saying it would be 5,000, but more than 5,000, because some of those 5,000 would have the allele, and then you'd have to get rid of them and sample more, but...
Yeah.
You guys are talking about 5, right?
Yes.
5 and 6.
5 and 6, they're kind of a pair.
Well, 5 is how you get rid of the purple seed from the harvest, and I'm assuming the harvest from woodstock, in which case you're either scouting the fields ahead of time and removing any plants with purple seeds, or you're doing it like he was talking about, optical screening after harvest. And yeah, it's more work, and then the higher cost is either absorbed by the farmer, the miller, the restaurant, or everybody.
Yeah, doing it after harvest, I would think would be difficult to remove the seed.
Well, you'd
be surprised that color sorters are really.
Yeah.
Yeah.
I was gonna say, run it through a machine.
Yep, and I just cheated and said you'd rent the service of a third party to do the optical screening.
There you go.
Yep, I'm a big cheater.
The way it's worded, it says eliminate purple seed from next year's. Oh, I guess from next year's harvest. I was thinking it said before harvest or something.
Yeah. And then I just said that I think what he's getting at is that you can eliminate it you can get all the purple seed out however you do it, and the heterozygotes are still there. You don't see them, and so they're always going to perpetually be there, and so on and so forth.
Yeah.
All right, don't be mad at me, but I'm going to back up a little bit. You guys, the probabilities, I mean, we're figuring out the frequencies, but the probabilities stay the same. Right. I mean, it's asking for 90. How many seeds will be sampled to be sure 99% you'll be able to find it?
I get the feeling with him that in number 3 we're supposed to figure out different numbers and it's supposed to be going down. I'm just saying, I know why you guys did what you did. I understand, but I still get the feeling he wants us to do it off of that stupid Fisher table.
Yeah, we had this discussion for a while too.
Yeah, I feel like if he's saying it's in Hardy Weinberg, he's saying it shouldn't change, then it doesn't make sense for it to change from year to year. But at the same time, I feel like the question, I want to answer it with different answers for each year because it just doesn't seem right to say the same.
Yeah.
Yep. But I don't know what the thing is I'm not sure what he's aiming to teach us here, that it doesn't change over all those years because of Hardy Weinberg, or that it does change because the alleles will, that the Fisher table, I guess I don't understand that.
Yeah, we were talking about that and about how it says that the Fisher table is based on fate of a single mutation, so that perhaps it's based on if there's only like one allele of that mutation in the whole population.
Yeah, I don't know if we're necessarily supposed to use the Fisher table for this. Because he never actually, like...
I'm not trying to make it worse. I'm just bringing it up. I'm saying that he was talking about using two different tables for figuring us out. One was the SEDCO paper one, so we get method 3. And I thought the other one was the Fisher, so we could get a percentage that we could plug in instead of just the allele frequency. I'm just saying I'll work on it here, and then I'll show you my work and see what you guys think. I just get that sinking feeling.
I understand exactly what you mean.
Damned if you do, damned if you don't.
I want to get this done because I'd like to have some free time because I'm kind of burning out again.
If you want a weekend?
Oh my God, wouldn't that be nice?
Getting to the point where work's going to be really busy already, and managing both, I'm already, I don't even care.
I'm just glad basketball season ended tonight because that takes a load off of my plate.
Are all 3 of these assignments due
Sunday night?
Yeah.
Sunday night. Holy shit!
Yeah.
And then we got
due sooner than usual.
What?
And then we've got 2 ALAs next week, and then we've got the next exam.
What?
And then we get the week of spring break off.
Yeah, okay. I asked about the 3 assignments this week, and he said we usually do 7, 8, 9, and 10 in 1 week.
Well, admittedly, 7 was stupid easy. I mean,
Yeah, but you spend at least a day looking at it and trying to figure out what you're supposed to do, so...
Okay.
Yeah, I think that I could probably do 5 and 6 on my own, and I'm kind of...
Yeah, I'm good with that. If we want to move on to 7.
Do the tough stuff with each other, and then we can revisit 521 in our brains to answer 5 and 6.
Sounds good to me.
Without altering milling properties, describe how to increase the frequency. Okay, so that's just another theoretical question as well, really. I think. Select purple seeds, do quality tests, do a separate increase and an isolation if you can.
Are you talking about for 7?
Yeah.
So on Tuesday, he did say that the C1 allele is linked to other qualities, such as the milling properties, so you have to be aware of that.
just as long as you mention it, I think it's fine. Meaning, here's what I wrote for number 7. I'll just read it straight to you guys. You could simply increase the frequency by selecting only the purple seeds from harvest and grow them in an isolated field in both Mexico for increase and in Woodstock for production. So that covers kind of the isolation. This could be accomplished by individual selection in field or by using a third-party optical screening service, my big cheat. Again, this would require some amount of investment and time to segregate the purple seed in an isolated land to grow it on. Now, because the purple seed are only recessive for the C1 allele, this strong selection pressure should increase the frequency to 1.0 in 1 year, as the C1 allele would be the only one in the new germplasm. This assumes that the purple seed has the same flavor, milling properties, and yields as the normal cultivar. If there are differences, then a breeding program would have to be established to create a purple seed variety that would perform as well as the normal cultivar. All my cheats are in a row.
Yeah, my initial thought was just to basically say that you would select only purple seeds and make the assumption that it's not linked to any of the milling properties or yield, because it doesn't specify that in the question.
And as long as you mention it somewhere in there and then say, hey, and we'll establish a breeding program to figure it out, I think that covers the bases. If he wants more from me, he's got to specify it better in the question or something. I don't know.
Yeah, we don't get the same assumptions that he does.
Well, I don't think we're PhD students on campus, and so we're not exposed to nearly as much as what what he expects from everybody else. At least that's a feeling I get. Which is fine, as long as we don't get graded for, less for not being PhD students on campus.
It's fair. We're not PhD students, so they shouldn't expect as much.
I'm just a little baby learner. All right. Should we look at assignment 9?
I'm ready.
Yep.
Okay.
I have to the font first. It's still in Times New Roman, and I just cannot handle that.
Okay, so has anybody started this or just starting?
I'm just starting.
Okay. So I had gone through and created like the Excel file for the frequencies.
All right. So sorry to go back to this, for ALA number 8, for question 4, you guys are saying if it's in Hardy-Weinberg equilibrium, you have 1 probability that purple seeds will exist, but how do you figure it out otherwise? Meaning it's 0.02 if Hardy-Weinberg exists, but how do you change the allele frequency if it doesn't using method 3? Any ideas? Oh, I suppose the allele frequency is that number, and then you just square it, right? Hello? Okay, somebody's there. Good.
Okay.
I'm gonna work on it just for a second, then I'll show you. Sorry. All right, who's ready to see what I got to share?
Sure.
So there's what I got for 3.
Okay, so for the second part, you pretty much used the Fisher table, right? Got those values and then multiplied that by the 0.135, and that's how you came up with your Q value?
Yes. Well, this is the actual number after I multiplied it times those frequencies. Hold on for a second. This is the actual table that I figured out. So there's the frequency of the allele. And then you take that. So right here, this is the formula, the one that we've known about.
Yep.
So you go over to this side, 1d6, yeah, right there. Because we know what the allele frequency in the first year is because it's what it is.
Mm-hmm.
So anyways, that's how I figured it out, all the way down through 10. And then that's it. Don't pay any attention to this other stuff. This is all wrong. Like way wrong. Like Zach is right and I'm wrong. But anyway.
Okay, so you just took that updated value after you plugged in the 0.135.
Yep.
Okay.
So this is the number that I can. So at the 10th, the number that I plugged in for the method 3 equation is 0.02. And I can show that as well. Right here. So it's a mess. So the formula is down here. This is a formula that we used for the question 2, question 3, whatever it was.
Yep.
And then I just put in. So there's the allele frequency straight up, and then these are the numbers from that I got from the Fisher table, calculated through that. And so then here are the seed numbers that I have. So that's how I got the numbers that you see down at the bottom there.
Okay. Yep. Nope. I'm following.
Okay. Does that make sense?
Yeah, I think so.
I mean, that kind of covers
that's where
both
I
our
was
bases.
Yeah, because that's what I kept debating back and forth, whether we did it that way or if he said it is equilibrium, then the other one makes sense. But yeah, if you present both of them, then
yeah,
you can't go wrong.
And then here's what I have for number 4.
Okay.
But I think that's the answer I originally had for that question as well.
Okay. Just so long as you guys have seen it and it doesn't like look too stupid, then
Nothing about this is scary or jarring.
good. I'm going to call ALA 8 done. Dang it. It's creepy scary. Yeah. Oops, I forgot to save it. No, wait, I don't want to be like Tyler. Tyler, I will never forget that. You erased all that info. Oh, it doesn't sound like he's here right now. So, moving on to ALA 9. You guys are just creating your Punnett squares?
Yeah.
Yeah.
Did you use 0.22 for R?
That can change. I think that's the whole point. I set it up like he set up his table.
Yeah, I did the same. So
Except I'm only partly done.
Okay. Because I was thinking for the F2, the 0.5 was what we wanted, right? And then if you set up the calculations like he's doing in the lecture, like you're taking the F2 and then adjusting off of that.
Yeah, but you should have it set up to where, yeah, you're right.
Yeah. Because otherwise, I mean, you could change that every time if you wanted, but since you already have the F2, we're just calculating based off of that is how I did it anyway.
Yep.
Did you figure out the equations that you had asked about on the discussion?
Yeah, well, I know how to get the F3 for the first genotype.
Okay.
I've got that equation down. It's just a matter of trying to understand where the heck it's all getting pulled from. Why is, I understand why he pulled the number that he did from, I'll just share this. It'll make it easier to explain it.
Sure.
You guys probably already know this, but. So in other words, right here, he had pulled it down. He had pulled from this cell rather than putting in point or dividing by 16 because this will always be 1/16. So that was kind of a nice shortcut, I guess, in a way, once it was explained.
Mm-hmm.
But after that, I think I've got this one figured out. Yeah, this one's correct as well. And he's just saying you just add those two together.
Oh, so you're using 0.2 for the R.
Well, just for right now. The nice thing about this is the way it's set up is I can change it to 0.5, and then everything shifts, just like he had it done.
So are you using 0.2 off of like this actual ALA 9? You want 0.2 or?
I just put it in there because when I was talking with them, we talked about 0.5 and then 0.2 based on yesterday's lecture.
Okay.
He was showing how it changes. That number can be changed as needed.
Okay,
Nice.
but for the F2, you're using the 0.5.
The F2 is based off of whatever's in the cells. So this F2 right here is based off of this cell right here, because that's the only one that it pulls from. You see what I'm saying? That's the only place that you get your number from for your for that F2.
Yeah.
And then when you go to this one, it's those. And this, because your F2 strictly comes from all this. That's probably why he did that. Okay. I don't know why I don't have that. Anyway, there. It's just a lot helpful because you know where it is in the F2. The problem I'm having isn't the F2 stuff. The problem I'm having, is that right? Yeah, that's right. Because it's that one there. This one is based off of those two, and then that one there is that one. Yep. So I've got all of that. The problem I'm having is where do you pull all of your F2 or F3s from? I know I got the first two right, but then just trying to figure it all out that's where I was asking for a shortcut.
Okay. Yeah, so I mean, I have mine filled out, but it was just going through line by line and seeing which genotypes worked. I can share mine if you want.
Sure. Well, and the thing is once you get the F3s figured out, you can just drag it over and
yeah, exactly.
Yep. Yeah, if you want to share, I just want to see if stop sharing. I just want to see if mine matches up to yours first, and then.
Okay, so F3 for the first one, homozygous dominant. Is that what you had? 0.14063.
Okay.
And I can highlight everything.
I'm just looking more at like divided by 4, divided by 30. There we go. Divided by 4 plus divided by.
So basically use the homozygous dominant, and then anything that's gonna show that phenotype.
Yeah.
Yep.
So what do you have for the second one for the F3? So yeah.
So anything that's got big M1, little M2, so it takes those two frequencies, and then I just had 2. That would contribute.
So, and is there a reason? Oh, I suppose you need to have them all. Yeah, I'm just wondering, E14 has to be what it is as well? E14. It would be your D31.
So I was thinking, because that heterozygous one is going to, well.
Yeah, because that all has, everything that is in the F2 column needs to move to the F3 column when you're doing your F4.
Yeah.
All that. That's why I understand why you keep the one up in the Punnett square locked, but I think all the other ones have to be mobile. Does that make sense? Because your F4 is based on your F3, not your F2.
Oh, yeah. I changed that in the later. Oh, no, maybe I didn't.
Just wondering.
I changed it manually after I did that, I think.
Oh, okay. So so for the third genotype, what do you have in that one? That's where I think I started having.
Otherwise, did you have the same thing as me for the?
Yes.
Okay.
Yep.
So
You have, okay, yeah, see, I knew I was going to have problems with this.
It's my frequency rate, though.
So
I'm not sure I have the right one selected in the top.
Well, to get the, yeah, you're right. The first one wouldn't count because you got to be able to get a small M2.
Yeah.
And
But then
yeah,
does
see,
that bring
this is where I get screwed up.
in D20 and E20? Okay.
See, I was thinking that it was based on the exact same formula as the first genotype, since it's got the same number at the F2. But it's got to be based on something different. So if anybody has any idea what the hell's going on to help us out,
So I
throw
think
in.
it's this one, right? Because that's the only one that gives us big M, little m, little m. So I just had that shifted.
Yeah, that's the first one, I believe, isn't it? Or is that?
No, so now I went on to big M, little m, big M, little m.
No, I'm sorry. What I'm saying is do you select? See, this is the hard part. Is I don't know how to figure out what goes where.
I'm sure.
And so, if I go into the
one
Punnett square, yeah, if I go into the Punnett square, there's multiple ways to get. Well, you're right. No.
Yeah, because you're looking at the genotypes. No, I don't think I don't need that big M, because that's not going to give me any little m's. So I need
right.
this guy. Yep. So instead of D27, I need D32.
Now, do you have it at all, or is it the same frequency?
No. Do I have what?
Well, for the first frequency, you can never get anything different.
Yeah.
But for the second frequency, can you? I suppose you can't get anything different, can you? Can only from itself. It can only create itself.
Yeah.
So that's why it's not divided or anything like that. See, this is one of those things where I wish he gave us the stupid formula. Because we dink around, we spend a lot of time just figuring this stuff out. And it doesn't, I'm not sure this is really helping with my education.
Yeah, no, I completely agree. Okay, why did I do that? I'm missing part. Okay, now I still have a little work to do.
Which one's going to have the smallest amount of this stupid stuff? Probably that. Okay. All right, if I have this right, I'll try and translate it. Okay, D29, you have right there. Okay, yep, I have D29 plus D32.
Oh, no, that's still off. Okay, I don't want D30.
You're not adding, you want to add in D28.
Yeah, that's the one that's missing instead of D30. There we go.
That's giving you your number?
Yes.
Okay, so D29, okay, blah, blah, blah. Yep, that one. And then you have 32. Yeah, you went
So everything that's got
I
big,
just-
little, big, little.
Yeah, I just kind of
Yeah.
swapped them back and forth. But what I'm looking at, okay, divided by 4, because I'm just trying to get the pattern down. So you divide by 4 for the one where it's only one allele is switched. The second genotype. So for you to get the third genotype, it's only 1/4 of the allele of the next set of recombination is you're only going to get 1/4 of them, which is going to be big M, big 1, little 2, little 2. 'Cause it's
Yeah, that's.
yeah. So that's why it's 1/4. And then the next one, you go where it's split 50-50. Big 1, little 1, big 2, little 2.
Yep.
And that is 31, but that's the one you have times E20. Why E20 instead of, well, I
So,
suppose it's the same
because
thing. It
it's-
doesn't matter.
So I went, the one that I multiplied by E20 is the completely heterozygous one. I use that for each generation as the one that I multiplied by it.
Okay. And my question is, why did you choose to put D28 where it is inside the parentheses instead of D32? Is that just because of the allele frequency or the alleles that are in there? Because they seem like they would be the exact same thing.
Yeah. From my understanding for this, it's the exact same thing, but I get what you're saying. Because yeah, I'm not entirely sure.
Okay, yeah, neither am I.
I wish I
That's
could
kinda
answer
where
it better.
Well,
I figured out enough how to do the equations, but I agree, like, the actual interpretation, like, I'm still struggling a little bit. That's why when I responded, I was like, I don't know if I can explain this.
Okay, yeah, I'm where you guys are now, and I'm trying to figure out what you're doing with the equation.
Okay, see, one of the things that's different is behind D28, I have a parentheses, and you don't in that equation. Yeah, so there'd be a parentheses there, and then you get rid of the one on the end, the very end. That'll match the formula that I have. But
Okay, it still gets the same value.
Okay. That's where I was getting screwed up. Okay, so E14 divided by 4. Well, yeah, if you can you click on the line again so I can see the colors? Thank you.
Yep.
Because I swapped 2 of mine out. I'm just going to match mine up to what you've got. Just so then I can look at this a little bit easier and not cry. Okay, so blue, red, purple. See, you've got stuff all swapped out all over the place compared to what I have.
As far as the numbers in the equation? Or do you still have the same, like you're still selecting the same genotypes?
I'm selecting the same genotypes. They're just in different order, and I wanted to see if that makes a difference.
I don't think it should, because you're just adding them together, as long as you have the same one being multiplied.
Right, so now I got it color-coded the same way so I can double-check all the same spots. So
It was just me playing as I went back and forth, like, which one do I want?
Yep. And then because once I see this, I can decide, or I can basically sit and say, okay, I understand that. You know, you're dividing by 4 for that because of this genotype setup. You're dividing by this, and then you divide by 16 because of that. Okay. All right, yeah, that one's the same. Now we get to move on to the next genotype, which should be, there should be 2 cells for that, right?
Yep.
I'm going to figure this out one way or the other. I don't care. So the difference is you want to pull the actual cells, and they should be should be this one and yeah. Okay, this is starting to make a little bit of sense to me. An E14, which is, I like how you already have your expected frequency and everything. That's great. I'm not even yeah, lovely. So, okay, yep, that's got to change to that. That divided by 2 because you're going to lose half. Because you have the first allele is 50-50 for recombination. And then why do you have D31 as, oh, you said you went through and changed it manually. Got it. Yeah. You want to drag that otherwise.
Yeah.
And so that's, now does this make sense to you? Or are you just going, as long as I get the right number, I don't care? Because I kind of can go to that point right now.
I think this one makes sense because, yeah, now you're multiplying. Like for the heterozygous, that's what I was always using as my multiplication factor, and then multiply that by the frequency that's expected. And I have 2 different frequencies that segregating there. Big M, little m, big M, little. Oh, wait a second. Big M, little m, big M, big M. Or excuse me, M2, M2. So I would want D21 and F19. Right?
Yeah, that's what I was using.
Yeah, so I had that off yet. But otherwise, that makes sense to me.
Well, the nice thing is once this is built, then we can cheat and never, ever have to make another Punnett square ever.
Yes, hopefully.
Supposedly.
Yeah, just don't lose it.
Yeah, no
Don't
kidding,
save it as a CSV.
that's just evil.
Yeah. Okay, and I guess this one I just divided by 4. Because it's going to segregate every time? Why did I know? Is that right? Or that should be...
Okay.
Include... I'm sure I probably should do something differently up here.
Yeah, it looks like basically it mirrors. Once we get down to the what you say is 4, right there, then once we get to that point, we are good.
Does this one look good to you?
Let me see. Which one is that again? That's the one underneath. What's the one above it? That's the one I'm more interested in.
The one above it right here? Oh, you want to know what the value is here.
That right there. You just have D31 divided by 4 because you can't get that genotype from anything else. Is that right? See what I'm saying? Or is there anything that comes from that? Because I thought the reason that this was such a big deal is because you get those 4 diagonals. But I think you're right. I don't think that you can pull a big M, little m, or big 1, little 1, big 2, little 2 from anywhere else. I think they all funnel into that.
That's what I was thinking. And then it's just gonna reduce each generation.
Yeah, and there's 4 cells, so that makes sense. Okay, I'm on board with that. So
Okay.
that equals that divided by 4. If it's that simple, I can live with it.
Okay.
I'm also doing sums at the bottom to double check everything because, like you said, that should
Oh yeah.
come to a 1. Yeah, it works out to a 1. So what the heck?
Okay, so that one just drags across.
All right. So the one underneath it, that's what you wanted to look at next to have me double check.
Yeah. If you're good, I think I'm.
Yeah, highlight it. The colors. There we go. Yeah, it should be the mirror image of the one that's 2 above it.
Yeah.
So
Awesome.
the genotype 4, that should be that, and except your box is up in the
Big. Gosh dang.
the Punnett square should be different.
Yeah.
But it's E22 and G20 for you. E22 and 20.
No, not on this one, because I still have Big M here.
Am I looking at
Right.
the right? Yeah, but that's why you do the G20. Because you have Big M over on the other side, but only one Big M.
Oh, okay. Okay, so G20 instead of D20.
It's basically the mirror image of the other one, yeah.
And
E22.
D. So change the wrong one. There we go. Okay. Otherwise, good.
Yeah, I think so.
Okay.
I think, is that one good? Yeah, that's the one we just did, isn't it? No.
No. Let's see. I've got something off here.
Okay, this is the one I'm working on right now, too.
Okay, let me fix mine. I've got a little big. Oh, no, maybe this one. Okay, no, I think that's right. Except for the top part.
So I'm trying to follow along with what you guys are doing, and I'm a bit confused. So it's like the one next to it, and then the one underneath the one next to it, divided by 4. I'm not sure where the 4 comes from.
So that's just because, like, when you go to the next generation, you're decreasing the frequency.
Okay, and you'd go down by 4 each time to make up for the fact that it's okay. The grid is going to change how many columns there are.
You know, some days I think I'm smart. And then I come to this class. What am I doing wrong? Okay, can you third from the bottom genotype, so the one above that for the F3. Okay, so. Oh, yeah. Is that right? No, one more above. Your point 0.14063. There we go. Okay, so what am I doing wrong? I've got that. I've got that. Oh, I've got my green and purple swapped. Okay. So that and that. Let's see if this matches yours after I do this. See, this is what I mean, is that I swapped 2 cells out and I was getting the wrong number. Yeah, now it's back to being right. And I was like, how in the world am I getting the wrong number? So, yeah, this is just painstaking. Okay, so we can do the second from the bottom now.
Let's see if I might be off. D19. Or sorry, did you need this one?
That's what I'm looking at right now, just checking yours. If I can hit the right cell, I swear. Okay, so yep, there's the middle one, there's the bottom one, D30. Yeah, so
That's
34
off.
is the blue, there's the red, same as that, and then you're using, yeah, your cells up
I
above
need
are.
to, yeah. E.
No, that should be F. That should be F22 for you.
Oh, yeah. F22.
And G21.
Big.
That makes sense.
Yeah. And then, yeah, that was the last one.
Okay, what do you got for your bottom one again? Okay, so blue, red, purple, green, that's what I've got. And then, no, I've got to change my box. Okay, so all my numbers match all your numbers, it looks like, and then you just drag it over.
Let me know if any of the numbers are off. I need to take out my dollar signs and actually
I'm doing it
get
to
my
the.
information.
I'm doing it out to the F5. That's it right now. My F4 and my F5, I actually have 1.023, so something's off. 6. Maybe it's because I'm rounding. Do you have yours set to a specific?
Nah, it's just left it. I haven't played with it. It's at 5, but
Yeah, I'm still getting 0.02. Oh, why is that?
on which
0.8.
one?
Oh, yeah, there we go. That's the problem right there. I've got to check just a second. So, yeah, right there. That's my problem right there is, oh, why did that not, why is that E14 still instead of? Huh, go figure that. For some reason, it's, one of my cells got stuck. What in the googly moogly?
Yeah, 'cause so far all mine are staying the same.
No. What happened is in one cell only, even though it didn't have the dollar signs to keep it stuck, it stayed stuck on the F2 line instead of moving to the F3 line like it should have. Yeah, now everything's
Weird.
fine. That was bizarre. Okay, so. Okay, we created the Punnett square and we created the quasi 9-level genotypes. Now we have to do. You did the.
So I did this here, but I didn't really need to since we don't actually have observed phenotypes for this. Then just consolidated it.
Well, I guess I just copied everything he had.
Oh yeah, no, we don't have it for the assignment because all we have is what we can see.
Yeah, no,
I
think I have for. Yeah, I put in for. No, I didn't. I just copied what he had.
I think I might have that over here somewhere. If I kept it, maybe not. Yeah, I kept that as an example when I was making it. But
you kept his?
Yeah, over here I've got that. What he had as expected, but then for the assignment I took it out.
Yeah, we're all big cheats. We just copied everything. Wow, you did all this stuff already. I'm impressed. Good job.
This is what I did Tuesday night because I didn't want to think about ALA 8, question 3. I was going around in circles.
I'm going to follow your lead and delete out a bunch of stuff.
Yeah. Okay, so if you figure out your F3 column, then you can populate your 4 and 5.
Yep. And you can create a 6, 7, 8, 9, 10, whatever the hell you want. And then everything should change as you change your R value up above in your Punnett square and all that fun stuff. And now we have this beautiful, wonderful thing that if I ever lose it, I will cry. At least until this class is done.
Yeah.
Yeah, I don't know if my R is plugged into it, but...
The R gets...
So, yeah, I just plug that in the frequency, or in the table at the top that I created. So I have that there.
Go one cell above. Go one cell above that.
Yep.
Oh, the 0.25. Oh, you did that. I'll show you guys what I did if you want to stop sharing for a second.
Sure.
Because this is what he was doing. And that is right here in the cells, you do this calculation. And then it changes your frequencies as well.
I didn't do that.
1 minus...
your cell with your R value.
2 divided by 2.
Yeah, that's where I was saying that formula outside here on each one of them, that's where you get that from. So then you can figure out your... I thought that was kind of a neat little trick. So that's why this one is different. It's only divided by 2 instead of the 1 minus. And it just follows that on the side. And then whenever you change your R value, it also changes your frequency values or whatever on the outside of the Punnett square box. Everything changes. It's pretty slick.
Okay, so it's 1 minus the...
1 minus the R value cell divided by 2.
Oh, I put the wrong R value cell. That's what happened. I was like, mine's not working.
Thanks for pointing that out.
1 minus...
I totally stole it from him, by the way.
Oh no, mine's just like completely corrupted now.
What?
Everything has no value.
And then you have to set your Punnett square up properly.
Maybe that's what it is.
1 minus...
Does that make sense?
Oh.
What you see?
Yeah, mine's working.
Okay, I'm going to stop because I'd rather have you put yours back up. that you know what's going down, Charlie Brown.
For once.
Hey.
Sometimes with this class, I feel like I do not.
Oh, you are not alone.
Okay. So did you want me to go over these, or?
Well, yeah, I wanted to see what your thoughts were on this.
So I basically just went up here and was like, okay, which ones am I going to see dominant M1, M2? So everything that would show me that phenotype is what I included down here.
Okay, for each one, and you just summed them together.
Yeah, that's...
Okay, let me try this first.
Okay.
Oh, you did it that way. I shouldn't do a sum. That's a bad idea. So anything with a capital allele, possible, doesn't matter what the second one is.
Yeah. Because, yeah, I figure we're looking at what we actually see, so.
Yeah, and that's kind of what he was getting at, too,
Yep.
was these are all getting grouped together. They're sneaky, that's what he said. What do you have your R frequency set to? Way up above.
0.5 still.
Okay, I want to change mine back to 0.5 so that works.
Oh, yeah.
I want to make sure, okay, yep, 0.5625, that works. So this equals anything that's an M1 with the two little guys. See, this is why I like having you around, because now I figured that makes this so much easier. I could cry.
That's what was wrong. I had R equals in front of my R value.
Oh, okay, yeah.
I was like, where did all of my numbers go? It's gonna be okay. I'm behind.
You are fine. You will catch up with no problem.
I don't know. My family's coming to visit this weekend, and I really wish that they would not be. I don't have time for relations.
Well, I feel you. Boy, I'm glad that I got super lucky in that trip I am going on with these high school kids. Fell on spring break. I am so happy, or I'd be crying my eyes out.
Oh, yeah.
So do you do the same thing with the F3, F4, F5, just drag it over?
That's all I did. So that way it just went off for everything I had
Yep.
up above.
Yep. We match up.
Sweet.
So that makes that easier. And then because you have your ASCII over at the side and the observed.
Yeah. So I just did that value divided by the number of total plants.
So I've got to change out some other thing. Why do I have 421? Is that 10? Yeah. So I already did it for 10, which I shouldn't have. Did you do 10 down below?
What do you mean 10?
ALA 10.
Oh, I had started getting tables and stuff together, but I didn't get very far.
Okay. I'm going to do what? I'm going to get rid of that. Just gonna, yeah, I started building that table down there too.
Yeah, I figured I'd get 9 done and then I can just move it over.
I'm a total nitwit. Because I swapped them, basically. I put ALA 10 up above.
So what was 10?
Don't even worry
Oh, yeah, much higher, yeah, okay.
Yeah, don't even worry about it. I'm going with what you did. Yeah, I'm kind of stupid, but that's okay. The nice thing is, I'm getting my midterm for Agron 523 done a lot faster than I thought. Are you in that?
No, this is my only class.
Okay, well, good. That's
Hey, I'm amazed you got 2 going.
And I'm doing my creative component.
Yeah.
Because I'm bored, you know.
Oh my goodness.
And my family. Don't even. If I seriously knew that this is how the stuff was going to go down when I started this class, I'd no, I can do without a master's.
I don't know. When I started this class, I thought that, like, do I really want to finish?
Yeah, this particular class? Oh, yeah.
Have you done a lot in your midterm for 523, Jacques?
Have I? Sorry, what was that?
Have you done a lot for your midterm
Yeah,
yet?
yeah. Chance is my partner, and he's a real go-getter, so he's kind of pushing me, and I'm like, okay, sure, I'll do this. So we're already kind of have our 2-page paper written up and all that stuff.
Oh, wow.
We are on. It's not that bad.
Yeah, I haven't My partner and I, we're both, I don't know, we're going to work on it tomorrow, so.
Yeah, the thing is don't treat it like, Chance has been talking with Dr. Luberstedt quite a bit. Don't treat it like just a back crossing. The big key is you have to work in other other trait selections as well, so that you keep that genetic gain every year going.
Okay.
Yeah, that's kind of the big thing.
Okay.
So, how did you figure out your expected at the F2? I just want to make sure I got this right.
So for the F2, I just divided the F2 value divided by the number of plants we had.
Oh, that's right. Thank you. I don't have that sum, so that's where I was going wrong.
Oh, gotcha.
Yep. .00. Well, no, I did something backwards. So I'm gonna say I'm an idiot. Why did I do? Okay, can you highlight the cells?
Yeah.
Make sure. Did I do that right?
Or do you want the cells?
No, I did that right. Why I'm not getting 59?
Do you have 0.5625 here?
Yes.
Oh.
Okay, so I made like a stupid mistake. I divided instead of multiplied.
Oh. Okay.
Oh, look at that. So what did you get? What's
59?
your answer? 59. Yep, that's what I got. And then did you you wanted to drag those?
Yeah.
I'm looking at what you did. So 39 stays fixed. So you wanted to drag them sideways for your 3, 4, 5.
Yeah. Yep. So I did it anyway.
Okay. All right. So I understand, and then that always has to stay there. I got that. So let me see if I get the same numbers. Yeah, I've got to reduce. 59, 41, 33, 30. Okay. Simple enough. Now I can do this the other way.
No.
20, 20, and 7. Yay for math working. So ALA 10 sounds like it's not going to be that bad, he said. Now, that's coming from Mr. I can do the exams in 4 hours, but still.
Yeah.
Okay, 25, 26, 26, 23. Yeah, we got all the same numbers. That looks great.
Some.
And that all adds up to 105. So I think you did a freaking awesome job.
Sweet.
And I've contributed exactly some secondary help and a formula that I copied from him.
Hey, I copied it from him too. So.
Around the edges.
I just needed to correct some of my values. When they're all the same, it's a little.
Okay, so I've got that set up that you've got now for, I'm going to call it ALA 9.
Mm-hmm.
What's next? So you put that there. What's below this on your screen?
I don't have anything else.
I thought you had where's your colored stuff?
Oh, that was.
Or is that all the copied stuff that you did from him? Or
what colored stuff? This?
Yeah.
Oh, that was just when I was making my actual frequencies and finding what my genotypes were, and then I just moved these down here. It was just me visualizing it. Was all.
Okay, so it's not important.
No.
Okay.
So yeah. And then it was just on to all the questions and the assignment, which I haven't done yet. But before I stop sharing, did anyone else have questions on any of this?
I am so confused about how to fill in that frequency chart.
Up here?
Yeah, like where you have your genotypes, your expected, and your F2. So I have the F2 column.
So you have the F2, and you have this set up.
Yeah, and I have that set up. So I'm trying to figure out how to do the F3s. So I have like the times 4. So
Divide by
I don't
4.
have the first 2. I have this 3rd, 4th, and 5th.
3rd, 4th, and 5th. Okay. So for the first one,
I'm going to jump off for a second. I'll be back.
Okay. So the first one, basically, you're looking at all of your genotypes that are going to give you the dominant phenotype.
That's what's going on.
Yeah. So, like, you know that this is the one that you... So this is the one that you're actually calculating for, the dominant. So that's why you use the frequency from up here for the dominant. And then down here, you're going to look at, okay, so I know I got this, but now I get dominant contribution from this one, and this one.
So the one underneath, because it's dominant, divided by 4.
Yeah. Since it'll
or
decrease.
The one underneath is the F2. So 2 big M. And then plus, I don't have the same cell numbers as you, so it's making it hard to explain. That one.
Do you have the same order?
Same order,
okay,
just
so
lower in the spreadsheet.
How low? I could just put in a bunch of blank cells if you need.
My first value is on 11, so maybe I should just make mine lower.
Oh, okay.
I'll just make mine lower. That's going to make life way easier.
Okay.
So that I start with my first set on 27. I did too many.
Oh, hey. So I had emailed Dr. Beavis just on our debate on ALA 8, question 3, and I just got a response. So he said the Fisher table is for a rare allele in a large population, and that's why he was trying to communicate 200 out of 11,000. The Q frequency is not a rare allele, rather a low frequency allele. So a low frequency allele cannot be lost due to drift or small population size, but not likely to be lost for this population. And he'll clarify that again in class tomorrow. So I don't think then we need to do that Fisher table part at all, and what we did was right.
We're right. We're so smart.
Sweet.
D31 is a real value. There it is.
So you're telling me that he's saying basically the frequency is going to be the same at year 3, year 7, and year 10.
Uh-huh.
Oh, that's stupid.
It's a trick question.
This whole class is a trick question.
Yeah. That makes me feel better, though, because, like, it's like, oh my gosh, like, this makes sense, but it also doesn't make sense.
Okay, I'm going to give you ladies, a taste of how I feel about this class. When I was in high school, we had a joke newspaper that would last about 1 or 2 cycles before it got too out of hand and the teachers would close it down. And they talked about one of the math teachers' classes and tests. And they said, here's one example that we smuggled out of his class. And he said, and the thing was, it says, hold on for a second. So my daughter's very excited about this because I've told my kids this too. So it goes, if a chicken and a half laid an egg and a half in a day and a half, how long would it take a grasshopper in sheep's clothing to kick the dill seeds out of a dill pickle? And I'm like, yeah, that's this class pretty much right here.
Oh, yes. Some days I think I almost have it.
I mean, it makes some sense.
Yeah.
After the fact. I think the problem is he's expecting that we know how to do a lot of stuff. Like I know some professors that would have just given us the the table for all the frequencies and just said, this is just busy work. But now I'll remember how to do this forever and ever.
Yeah.
Maybe.
So that's
And
the
it makes
positive
us
side.
think about how we're actually getting them. I get it. But
I get it. I'm not into it anymore.
Yeah, I'm sorry, but Dr. Beavis really, and it's not a diss at all, really reminds me of exactly what he was talking about. He reminds me of one of the old math professors who knew how to use a slide rule magically and expects everybody else to have a passion to learn it, even though, we have computers and calculators.
So I have a question about putting these values into the F3 column. So I did that first one. So just to clarify what I'm doing for the next one now, so I'm calculating cell E28. So I'm still going to be picking the ones that are going to be...
no. So now you have to take into account that this is you have segregation in this allele. So you're also going to lose some in the next generation. So anytime you have a segregating allele, then you divide that by 2.
Yes, okay, divide by 2 because it's segregating, and that's because I have big M and little m in the second subset of information.
Yes. And then the only way you're going to get that again is from the completely heterozygous genotype, and that's where you add that in and multiply that by the 2 frequencies that would produce that. So the M1, big M1, wait, am I off? No, yeah. That you'd get your big M, big M2, little m2. So you've got 2 there. So that's why those are both represented.
Okay, and for these ones, you don't have to reference your table. Oh, yeah, you do.
Yeah, I
reference
do.
your table.
Yep.
Yeah.
So you're still referencing the genotypes that would give you that same, the genotype that would give you that phenotype, right? Yeah, I think.
Yeah, so
No,
it's like
that sounds right.
the one next to it, and then we're also divided by 2 because it's segregating,
Mm-hmm.
plus YD31.
So that is your heterozygous allele, and that's the only one that's going to give you a heterozygous allele at M2, little m2. So you're trying to find this genotype in the F3 generation. So the only thing that's going to contribute to that is this.
I just did something that made all of my values yell at me. Okay.
When aren't they always yelling at us, right?
A lot lately. Oh. This is probably I don't know, maybe I've just forgotten what the other assignments feel like, but this one feels extra nasty for me.
The calculating out of that stupid table from the Punnett square is extra nasty. It just is. I know I'm whining, but it really was intimidating.
Divided by 2. I see what I'm doing. Okay. You can continue now.
No, I'm done whining.
There. Now they're real. I was trying to calculate by a non-number column. Oh, but these numbers are not matching. Neither was my first column. So I guess I'll look at what I was doing wrong.
So everything here, do you have the same or no?
Everything in the first column is identical.
Okay. So this one is already different though?
Yeah, the first cell matched, but the F2 did not. Okay, so D27 times divided by 4. No.
Yeah, plus.
D28 plus D28 divided by 4 plus D30 divided by 4 plus D31 times F19, which is the first table value. So that's good.
Okay.
And then when I drag it over, I get 0.21 and 0.26. So yeah, they're exponentially larger.
And
then
you're using the same R value, 0.5?
Yeah.
Yeah. Huh.
Okay, let me see. What's going on?
I'll put it on this, or I
Yeah,
don't know
do you want to
what
share? Or
Yeah,
Okay, I'll let you.
maybe. Share Cassandra.
Yeah. Ooh. All right, so it's my table right now. And I moved everything so it would be where you guys had your stuff.
Okay.
Yeah, and then these are not matching. So this is what I have here.
So highlight your F4, because F3 looks right. So,
Okay, which one are you in? You're in your F4 on the first one?
F4 for the first column in the new table that we're generating.
Okay. You're in the F3. Yeah, that looks right.
yeah.
Now, let's see. Divided by 4. Oh, that's your problem right there. E31. So you should have E27 the way it is. Then you should have E28 divided by 4 the way it is.
Mm-hmm.
Then you have E30 divided by 4 the way it is. And then... Okay, so that formula looks correct. And in the right order, so give it a go. What did you get for a number?
0.21.
0.21 based on... Okay, that's because... No, her F3s are not complete yet. That 0.1875 is not right. The F3 in your second gene, that one right there is wrong.
Okay.
That one should be... No.
The
You
number
should-
next to it.
Divided by 2
D25.
plus...
D31.
That should be... Yeah, your D31 should just be a D31 number. It shouldn't have any dollar signs in it.
This is
Oh,
E20 and
you're-
E19.
So you don't want to use E,
No, I want to use...
the 0.0625 values.
Yeah. So I would want this to be shifted to F. And this to be
So that would be G19?
Yeah.
Yeah.
G, so it's that blue one.
Yep. And then your
There you
D31... No, go back up. This will screw up your calculations otherwise. That D... No, you got to go to your F3 of your second genotype. That D31 should not have a dollar sign in it. And that's so that it drags over when you move it over to the F4. there you
And
go.
that's going to make the other numbers change.
Yes.
So how do these aren't right?
0.0546. Yep, that's right. 0.029. Yeah. Now your second genotype is correct. Your first genotype is correct.
Okay. And then this third one, the number next to it plus 32 divided by 4, 8 divided by 4,
Gotta jump off for a minute.
divided by 4 times G20, because that's the only entry is big little.
Yep.
So that's good.
Looks good.
And then this one is done already. This is the easy one.
Okay, so in the one above, the F4 and F5, I have different, but is that calculating on something you don't have yet? If you just click on the F value, F29.
F29.
Yeah. Okay, yeah, so you're missing one yet. That's why. Okay. Nope, we're good then.
Oh, I see. Yeah, because I don't have that. So escape. And then this guy is going to be number next to it, and it is segregating.
Yes.
So I divide by 2. And that should be a bracket, not, plus. Plus bracket?
Yeah.
And then it is going to be the other segregating lines divided by 4.
Yeah.
So this is...
Or no. So since it's segregating, the only thing that will give us that genotype would be the completely heterozygous one. So you'd do E31 times your frequencies in the table above. So
and this is big little
G22.
Big little.
And I20. So G22 plus I20. And then multiply the addition of those two. Yeah, so probably put another bracket around the addition.
And that should make it happy.
Mine's 0.09. Can you open yours up again? So D32 divided by 2 plus, so you have E31.
Oh, so this should be maybe...
so it should be D31, yep.
Yeah. Oh, okay. I'm starting to see the patterns.
There we go.
Yeah, okay. So this will be this. And it is not segregating. Correct. So no dividing by 2, and then I'm gonna add it with the other not segregating.
Yeah, so everything that'll give you the little m, big M, little m. Or no, big M, big M. So like the one below it has a big M. So that could segregate out and give you the same phenotype.
Okay. And then divide by 4?
Yes. And then, so D30 would also be able to give you that phenotype.
Okay, no. I know it's not right. I'm sorry.
And then you'd take into account the heterozygous one.
The one that's in everything, the 31.
Yeah. Yep.
Oh geez, I put another equal sign. Do not like that. That is a plus, not an equal on the keyboard. That's a me problem, not a real problem. Okay, and then I need to account for what's in the table over top.
No, so the D31, since that's completely segregating, you'll multiply that by your frequency instead of dividing by 4.
Okay. And this is big, little.
Yeah, so I had H21, I think.
Yeah, it's the orange one. There, I'll have to pay it forward, and if someone else needs help with this table, it'll be my turn.
Looks good.
2 more to go. Okay, so the one next to it, it is segregating. Divided by 2 plus other segregates that could give me little big or little.
Yeah, so it'd just be the heterozygous, completely heterozygous allele though.
Just
or genotype.
One.
Yeah.
And then that's going to be multiplied by the place in the table.
Yes.
Of little, big, little.
Yes.
Little, big, little.
I think F22.
This one.
And I21.
The other white one.
Yeah. Go back.
Oh, sorry.
I think you need a bracket around the 2 that you're adding before multiplying.
Yeah, otherwise it's a different order of operations.
There we go.
Okay, so this is fixed. So it would only go by the fixed one then?
No, so anything that would be able to get you that little m recessive. So like B34, when that segregates out, you could get away from that dominant M2. So that would be possible, yep. And then so would B31. Or wait, add. What did I have? Okay, so I had 32, and then the heterozygous 131.
Okay, so rather than 32, 34, do 32.
So now you'd add both 32 and 34 is what I had.
As well as.
Yeah. Yeah, no, that's right.
And then add. Oh my goodness.
Last one.
And then I'm going to multiply it by table value.
Yes.
I'm not sure what the problem is.
I think just delete the parenthesis at the end, maybe?
These don't equal 1.
Okay, so which one's different? 14.09. Okay, so I'm guessing there's maybe a $sign or something off. Let me check all the F4. Okay, so F32 is different, I think. I've got 0.05, so what do we got? So, oh, D instead of E. Or no. Wait a second. In the F4, so the F3 was right. In the F4, no, you have E.
Mm-hmm.
Okay. Oh, you've got the F31. You'd want the E31. Because yeah, instead of using the value above where you're selected is highlighted, you want to change it F31 to E31. Because you're only calculating off the F3.
E31. Okay, and then I have this out in outer space.
Okay, so let's see.
What's going on?
There you go. So I had G and E. Let's see. So yeah, and it should technically be G22, not H22, I think. But yeah, your value's right. 0.5. Oh wait a second.
Yeah, that should be G.
0.54. Yeah. Okay.
So then, do I need to drag this over then to fix that?
Yes. 5. Okay. What? Oh, the bottom one's off also. So I have 0.19.
And I'm out in outer space again. Cancel.
Okay, so otherwise I think it's just how yours is rounding, because I have 5 decimals and mine is saying 1.
Okay, so I'll try going into the number setting and seeing what happens if I switch my decimals. Number. You have 5?
Yeah. Ooh, not quite. Okay, so what's the difference? 5, 4, 6, 9. Okay, so the only one, row 34, mine's slightly different. So I've got 0.054 in the F4 instead of 0.050.
Okay.
So I don't know why that is. Because the F3 value is the same.
J should be I.
Oh, you're J. No. Yeah. Well, that puts you over. Okay, go back to that. Okay, so I have F20. It would be H22 and I22 on that one. Wait, no, I'm looking one above you. Go up one row. The 34, F34, yeah. Okay, so for that one, I have what would be. I just messed up my calculation.
I-22 and I-21 seems weird.
Yeah, so I have, it would be H22 and I-21. Not that the value should be different, but this 0.65 is the same, the 0.09375 is. Why is it still coming out to 11? So I don't have that 0.11. What is different? E34 divided by 2 plus E31. Oh, bracket around the additions.
Oh my goodness. Thank you.
No worries. There we go.
Yeah, that's
yeah. Drag the one above it. Row 34 over. Okay. So I've got 0.029. So let's look at, is there a bracket again? No, we've got. So the second one from the bottom, G34. We've got F34 divided by 2 plus F31 times. You've got J.
Oh my gosh.
So H22 and I21.
So, like, did I have a dollar sign somewhere that just kept dragging?
Must be. Or missing a dollar sign since it shifted over column J. So the last one, like, I had dollar signs in both of the, like, the F31 and the I21. I had dollar signs there, so it wouldn't change what I was using from the above table since that was constant.
Yeah. So this is close now.
Okay, so the the very bottom one is slightly different is the only thing. So you've got J. Yep.
Yep.
Easy enough.
Kind of. Okay. That looks fine.
Okay, so FG33.
Okay.
G30.
What did I do? Oh. So it should be I-19 rather than 17. No.
So I had G22. Okay, so let me look. So I had, it'd be I-20 and G22. Yeah!
Once all across the board.
Sweet. All right.
All right, so we're part of the way into having tables.
Yeah. So yeah, then for below, all I did was add up all of the genotypes that would give me that phenotype, since we're not able to see the segregating alleles.
Okay, so I'm going to look at the assignment because it probably references that. Okay.
Yeah, because that's why we're only getting 4.
come in.
Yeah.
So now we're looking for the 66, 11, 10, and 18.
Yep. Because that's all we can actually see or identify. We can't identify if it's segregating at that allele. So we go from 9 to 4.
Okay, so there we go. Okay, open yours up again. Or open up the viewer again. So for expected. Oh, you didn't really put anything for that expected value. Okay.
Boy, that whole time I was talking and you guys couldn't hear me because
Not a peep.
Oh.
I'm a moron. Anyways, so Cassandra, you see what this is all about, right? You see where this is coming from and how we got these numbers?
Yeah, mostly.
Okay, yeah, these are all the cells that contain the F2 results for this genotype. Anything that's got two dominant M or large 1, large 2.
Okay,
So if you have anything with a large 1, large 2, you add it together. Same thing with this one right here.
The underscore is just like it doesn't matter.
Yep, it doesn't matter. As long as you have a single capital 1, you count it. And a capital 2. So that's how that worked. That was make that so much nicer. I was so happy.
That makes sense, yeah.
Yep.
That is what I need to add those. And then I'm just going to add the F2 value from above.
Yep.
Just straight addition.
Yep.
That's so elegant.
And the nice thing is then you can just highlight all this and drag it across.
Okay. So I already don't have the same. I'm just missing something. I have 3 values for the first one. I must be missing one.
Well, take a look on the screen.
Yeah, I'm vision impaired. I see what I'm missing. Thank you. Did you get the same values for the 11 and the 10 observation?
Yes.
Okay. Oh, is this going to be one of those? It looks like a pretty nice distribution.
Yes.
It looks like genetics 506, I guess is what I'm trying to say in a really haphazard way. Are we looking for little m1, little m2, just like within it overall? Because they'd never be on the same side. Never mind. Yeah. So the first and the last one are the same too.
Wait, what do you have?
So I got 0.56, 0.18, 0.18, and 0.56 again.
No.
Okay.
For the last one, I had 0.06, and then that all adds up to 1.
Been too generous with what I was accepting then.
Yeah, no, because this would be the only. You're just looking at what you can see. Like if you could see different genotypes for all 4 of these, you can only find the recessive allele when it's in that little state in the field. So we're looking at the plants and
I'm looking for recessive homozygous.
Yeah.
Double recessive homozygous. So it should be 0.06.
Yes.
And that makes sense where it would be that like perfect distribution.
Yeah. And then everything should add up to 1.
Yeah, assuming that there's no linkage or pleiotropy or stupid stuff going on.
Yeah.
That always happens in real life.
Exactly. So right now you're only figuring out what a normal population would have. And then when we divide those values by the observed 105, that's where you figure out if what you're actually seeing is off of what the standard expected rate would be.
Oh, so is this almost like the chi-square table in a really drawn-out way?
Yeah, this would be, yeah.
Okay.
Just making you get to it on your own.
So are we at the point where we're starting to do ALA 9?
Actually answering questions? Yeah.
Yeah. Have you guys filled in your expected or your logarithm columns at all?
So I have the expected. The logarithm columns, I wasn't sure how to do that.
Okay, what did you guys do for expected?
So that's where all I did was take that. So you got like 0.5625, divide that by 105 plants. So the sum of all your observed compared to what the standard expected frequency would be.
Okay, I got a negative number.
Okay, so you did 0.5625. Oh, excuse me, multiplied.
Oh.
That makes a difference.
I did that with percentages the other day and was like, what is going on?
So now you get 59.
These are going to be way better numbers now. Oh, what is wrong? Why do I have...
And I use $ for both numbers. That.
All I'm wondering is the way the wording is in ALA 1 number 9. Are we looking for the expected rate at the F5 or the expected rate at the F2?
So I went with the F5 because what did he say? This population's derived from the F5, right?
No, they're derived in the F5 generation.
Oh.
From a cross of 2 completely homozygous lines. So I don't know if that means that there were 2 lines crossed, taken to the or 2 lines that were taken to the F5 and then crossed, or if this is a cross of 2 and then.
Yeah, I'm taking it as we crossed it. This is the F5 we're looking at.
The F5 of the cross?
Yeah.
Okay.
Maybe I'll throw in the table of all my values just to be safe.
I would throw my tables in just to like verify what I'm doing.
Yeah, the only thing I'm saying is that at the F2 you get a really nice 9:3:1 ratio. At the F5 it's getting close to 1:1:1 ratio. See what I'm saying?
Yeah, and I was thinking that's to prove his point, because we have to talk about like coupling.
Yeah, that's what I was.
And that would allow us to.
So what do you think?
So if the F5 population is what we're comparing to what we observed, then it's completely off, and it's got to be in coupling because you're seeing 66 in the homozygous state instead of 30, which is what would be expected.
So, but if it was in repulsion, then you would see the flip around, right?
Yeah.
Where are you guys getting 60? Oh, 66 from the original observed.
Yeah. Yep.
Yeah. So in coupling, you have the main, the parental, whatever they call them. So it's got to be in coupling, because if it was in repulsion, the middle two would be much higher numbers, and the other two would be lower numbers.
Yeah.
The way I see it.
Because the homozygous dominant is more prevalent than it should be. Whereas occurring at a higher frequency. In a normal distribution, like how would you say that? Or in a Hardy-Weinberg situation, or?
Yeah.
Somebody needs to write this out and then like state what they wrote, because it can be a mess quick.
Yeah, well, I might just need to come back,
I only had two quick little
and then come back to it.
Okay, Michelle, what did you write? How about that? What do you?
I only wrote two little sentences quick and said the observed genotypes are higher than the expected frequency in the F5 generation. Therefore, the alleles are in coupling, allowing for a higher than expected amount of alleles to be linked during crossover. So I need to add more information, but very basic. I mean, it's 2 times, or we're seeing 2 times the rate of homozygous dominant than what we expect, or over that. So.
Yeah, but that's the question, is that for the dominant it's more than 2, but for the recessive it's actually less than expected. Is that still going to say, are you still thinking it's coupling? I mean, aside from the fact that the 2 recombinants in the middle are lower.
Yeah.
I'm just asking. I'm not saying I know anything.
Yeah, I'm still thinking that's the reason, because otherwise those would be able to break up more. So instead of getting those recessive recombinants, it's not crossing over there.
Well, we're not seeing that observe. Well,
yeah.
I'm going to stop talking.
I don't know. Does that make sense? Or?
Yep.
Okay.
Yeah, it has to be coupling. It's not distributing the way that you would expect. And then back to question 1, what were you guys putting for your table? Of all of this information, what were you putting in there?
I just put in the expected R at F5, and then the 30, 26, 26, 23, and I have that next to the assay and the observed box. It's 2 little pictures, but here.
Yeah, so I had assay, observed, the F5 frequency.
That's what I've got.
Okay.
So I kept the frequency in mine. So I just showed the frequency value was all. Otherwise, I did the same thing.
I was just gonna say about the coupling. I think that because originally the homozygous recessives would be such a low number, what is it, 0.0625 is the original frequency.
Mm-hmm.
And so the fact that that actually goes up would still put them in, would still show that they're staying together rather than being, I don't know, separated.
Yeah,
no, that makes sense.
That makes sense.
And it explains that part, which I was overlooking. Yeah, no, good.
Yeah, so my expected numbers are very different. Or not, well.
For F5?
Okay, it's the expected at F5.
So that's what we decided on the F5.
I would sub out A38 for G38. Then I get 0.15.
What are you doing?
I don't know anymore. For the expected, so it's going to be the original observed value
Yep.
times the F5 expected,
Yes.
which would be G38. So yeah, I'm getting 0.15.
So for F5, did you have 4 numbers, like 4 genotypes you were adding together and get 0.2822?
I added 4 numbers together and got 0.56 for the F2, and for the F5 I have 0.28.
Okay. So the 0.28 divided or times 105.
I think I see the problem. Now I have 18.6. I have these numbers in a weird order. That's what's going on.
Okay, yeah, because 0.28, I still get like 29 and some decimal.
Sorry, I haven't been paying attention. Where are you at? What are you helping with?
Trying to figure out her F5.
F5 expected is weird.
Well, share.
All right, just a second. Yeah, like the distribution is pretty similar, but it's not.
Well, let's
Like-
just take a look real quick. That's the easiest way to figure it out.
All right, so here's my little table.
Yeah, yours is, yeah, it shouldn't be that. Oh, wait. It's the same.
Oh, you're using 66, not 105.
Yep.
For all of them, it should be the 105.
Yeah, because
Yeah.
you're comparing what's expected to the entire population that you're looking at.
Yep.
Oh, jeez. That's why you guys had the dollar signs in it.
Yep.
Okay. I'm gonna stop sharing now.
Okay. So we've got number 1. We've got number 2, which we can talk about. So number 3 is where I wasn't sure.
Yeah, estimating the recombination frequency. That's the.
Yeah. Conditional on the coupling phase.
Well, we know
So-
that we are in coupling.
Yeah.
I like how it's conditional on the coupling phase, but it's coupling phase that we're in. So.
Yeah. So he already told us, yeah.
Yeah, well, sort of, yeah. Of M1, M2, and I know we talked about it.
You must first prove there is no disequilibrium.
Yeah.
Okay.
So, no thoughts?
Not yet. I'm looking through
All
notes.
Yeah. Okay. All right, I'm muting it. You don't need to listen to her. Well, I think our answer is on page 4. Bottom of page 4, underneath the graph showing the disequilibrium curves. Estimation and testing disequilibrium at 2 loci. Disequilibrium at the A and B loci is a comparison of gametic frequency with the product of allele frequency. And then we get to, and that's where it breaks all the way down to a chi-square statistic for the hypothesis of no disequilibrium can be based on z squared equals x squared AB. You guys see all that?
Sure do. Yeah, so this is like in 506 when you do your null hypothesis.
I just want to calculate it. We've got observed and expected, for gametes. Yeah, that's what we've got, right? That's our chart, or is that not our chart?
It's pretty close. Like, we have observed, we have expected, but
that's not gametes.
Broken out far enough?
Yeah. We got to figure out our observed and expected gametes.
Yeah, because ours is phenotypes right now, isn't it?
Yeah. Yep.
I wish I knew how he just like has those little like pop-in equations in the documents. If you hover over them to copy and paste, they're just like a little image. So slick. But he still uses Times New Roman.
What does that have to do with anything?
So fun. I find it hard to read because of the curves.
Okay.
Maybe it's just a me problem.
Well, we're not going to get any observed gametes because we don't have any observed gametes. So we got no way to. We just got to figure this out.
Would we break out the gametes? Oh yeah, because we don't know in our observed.
Exactly.
I see what you're saying now.
Yeah. Likelihood, I can figure out disequilibrium now. PAB. Allele frequencies we can figure out. Right? Yeah. My brain is shutting down, guys. I'm sorry. Somebody's going to have to think harder than me.
It's like, yeah, how do we break that down further?
Oh, the top of the page gives us our answer for ALA 9, question 2. A coupling heterozygote. Oh, dang. Yeah, heterozygote would be AB and occurs with frequency 2RU, and repulsion is 2ST. And RU is... That makes sense? See how that works?
Oh, which page in the document?
Page 3 at the bottom. You've got
in that
the
little
chart.
table.
It's got the RSTU for the actual frequencies. And then if you turn the page, if you go to the top of the next page, it says a coupling heterozygote would be AB, large AB, small AB, and occurs with frequency 2RU.
Yes, I see that now.
There we go. Disequilibrium is given by D equals D or DT, so D5. Okay, here we go. I'm starting to figure this out with my addled brain. So D E equals in the zero, D equals the RU minus the ST. That's the heterozygotes. I'm assuming they're supposed to be times each other, it looks like, unless I'm nuts. No way. Huh. Okay, here we go. All right. Let me show you this. See what you think. For disequilibrium, we have the equation on page 1, 2, 3, 4, right? It says D equals RU minus ST equals 0.
Mm-hmm.
That says they're in equilibrium. It can be shown, and then right below it, it can be shown after T generations of random mating, the disequilibrium is given by DT equals D0, whatever, right? So to figure this out, I do this at the F2 and the F5, okay? So at the F2, this is RU, and RU is R times U, right? I'm looking at that, and when I see RU, it's got to be R times U, because it doesn't say R plus U or R minus U or anything. It's RU, so it's R times U, right?
Mm-hmm.
I'll just do that, and I'll do this as the RU, so you can understand it, and that is the ST. So that at the F2 is the RU, that at the F2 is the ST. At the F5, they're equal, so they are in equilibrium. They were in disequilibrium at the F2. They are in equilibrium at the F5. Estimated. Or they should be in equilibrium at the F5. Sorry, they should be. That's the expected. Then the observed is I did that wrong, sorry. So there you go. The expected ratios are all in equilibrium, but the observed obviously are not going to be. They're way in disequilibrium.
And this is proof that they're in coupling, or proof of that disequilibrium for question 4?
The top paragraph is the proof for the question 2.
Okay, yeah.
Because it is occurring at least 2 RU.
Mm-hmm.
It's a coupling heterozygote.
Yeah, because we have a coupling homozygote.
Well, I found something cool. Is a comparison of the gametic frequency, which we have, right? And allele frequency. Oh, we don't have gametic frequency. I think we can calculate gametic disequilibrium if we work at it, and I'm just 2 steps in my brain gone.
Yeah, I think I'm about done for tonight.
I don't think
Saturday or what?
I was gonna come online like right after work tomorrow and try and hammer out a little bit of stuff, and then I'll be in and out on Saturday, and I really hope I don't need to be on here Sunday.
Sounds good. I can probably do like 5 to 7 or so tomorrow.
Yeah, that would be great, because
I'm going to be doing 523, the Zoom session with Dr. Liverstead at 5, and talking with my partner for a while, but I can probably hop over onto this after that.
Okay.
Well, we'll get a head start and tell you all the stuff we figured out while you were
That would be fabulous. I'm all for it. Well, we got to ALA 9 number 4.
This is the most I've had done by a Thursday evening yet.
Yeah, and 10's supposed to be easy after we finish 9, so we're almost there.
Yeah, like I think for 10 we might just have to like pop
It's
out
just the
a couple
maximum
numbers.
likelihood estimate of recombination. Well, that's all the log stuff. That should be easy.
Yeah, like we have the table started basically.
Yeah. In fact, we practically have it built.
Guess what, everyone? We're gonna have a weekend.
Woohoo!
So when did you guys say you were going to meet?
I'll probably be on around 5 tomorrow.
Okay.
Yeah, and I was gonna do like 5 to 7.
Yeah.
See what gets accomplished.
Try to have a
And
little
then
bit of a Friday night.
A little
Boy,
bit.
wouldn't that be nice?
It's my partner's birthday party, so I guess I should go.
I think I'm supposed to go to a concert tomorrow night.
Yeah,
I'm
we all
supposed
got
to go see a
places.
movie this weekend with my family.
We are all going to be able to do these things.
Oh, Cassandra, here's something that you might like. You know who Red Green is, right?
I know who Red Green is, yes.
He is going to be in Grand Rapids, Minnesota on, I think it's April 8th. And so I get to go see him.
That is very Canadian, and I'm very proud of you right now.
Yeah,
I didn't know that Red Green like travels and does shows.
I was gonna say,
yeah.
I kind of didn't know he was still alive.
I was thinking the same thing.
The pitch was that he says retired in 2009 and came out of retirement due to lack of money, and so this is kind of like his farewell tour kind of thing. So
He couldn't afford any more duct tape.
Ah, there you go.
Once they started making multicolored duct tape, it really just ruined the game for him.
Yeah. Yeah. But anyhow.
Just stepped up his game.
It's true. It could have been very. That would have really pleased the ladies, because that was his thing. Is like, if they don't like you because you're cute, at least they'll like you because you're handy.
Yep.
Yeah. You're not handsome, at least you'll be handy.
That's
Yeah.
right.
Yep. All right. See you tomorrow night.
Yep. See you then. Have a good night.
y'all.
Yep.
Yeah.